Cloud. We're going to go ahead and start. All right. So we are working today on instrumental variables and regression discontinuity design. And the goal today is to get through this and to get through what I'm going to just offer up as some advice about how to present your instrumental variables uh, results in tables and figures. Now, I can't speak for what industry is looking for, but I suspect that industry is uh, will benefit from the exact same advice. Okay, so that's my sense is that industry will benefit from the exact same advice that I'm going to give about what figures you might kind of or the not the actual figures because each of the figures that you're going to create using instrumental variables, first of all, as I'll get into, the data visualization is crucial in causal inference. It's absolutely crucial, and it's uh, doing causal inference, and all you end up doing is just reporting a bunch of tables with stars, with coefficients and stars, is a way to get people to just literally not even pay attention. So we're gonna get into some advice that I think is important. Real quick, let me do one thing here. I've just now realized that we need to fix the audio. Okay. All right. So let's get into this. Let's get into where we were. Um, we were talking, so we did background and intuition on instrumental variables. We talked about this idea, very vaguely about we had the DAG structure that we were looking at here of what a good instrument is, which is you have here the research question. You've got, generally speaking, some sort of confounder that you can't account for using a covariate adjustment strategy. And you've got a third variable that's independent of it. If you could run the regression of the instrument on that confounder, they would be completely independent of each other. They would have no correlation whatsoever. You can't do that, though, because you don't have it. If you had it, you wouldn't be using instruments in the first place. So that's the thing to remember. But if you could run the regression of that random variable, because it's a random variable, if you could run a regression of that random variable onto that instrument, it would be independent. They would be completely uncorrelated with each other. You wouldn't want to control for church, though, because church is a collider along that along that path. You would just say run that regression, they'd be independent. Secondly, another attribute of a good instrument, and this is what we're going to kind of hopefully spell out a little bit more, is that it both should be correlated with the outcome. It just needs to only be correlated with the outcome through the treatment. So you have to kind of remember as we're going forward that there is a sense in which instruments are irrelevant. They are not interesting in and of themselves. They are only valuable insofar as they are assigning the treatment. That's what makes them valuable. They cannot be themselves. They cannot be themselves causing the outcome. That's the thing to remember. Insofar as they cause the outcome, they sort of become interesting in and of themselves. All right. So you have to kind of remember, no matter how clever and how proud you are of your instrument, and that's what's going to happen when you find a great instrument, you will be proud of it. You will be impressed with yourself, as will others, because it is sort of like solving, like a Bitcoin mining. You sort of end up kind of feeling like I put in all this hard work and I did it, and a lot of people fail at it, and I did it, and it took shoe leather, and it took time and it took really careful thinking, and I figured it out, and I'm proud of myself. But you have to remember, uh, it's only valuable. Its only value is to identify that causal effect. You can't lose sight of the research question. The research question is what's important. The instrument is only important insofar as it's causing random variation in the treatment. And so you have to let yourself always go back and remind yourself that this is a study about the treatment's effect on the outcome. And the instrument is allowing you to find random variation in the treatment. And that's why it's special. And that's why it's valuable. And in the history of applied microeconomics, it's kind of, frankly, always, it's for a long time been a little bit out of order, where people almost thought that what made a project valuable was the instrument as opposed to the research question. So that's just something for you to remember. I think you've got to, that's why, in any project that you do, in any project that you work on, just don't lose sight of the importance of your research question. If your research question is not important, but you have a great instrument for it, you haven't really, and I'm speaking to myself too, you haven't done anybody any favors. Okay. And I remember when I first got to Baylor, my department chair, he just made this passing comment. I don't even know if he would even remember it. He said, the good papers and the bad papers that we work on, they actually take the exact same amount of time. Okay? They take the exact same amount of time to do them, and they take the exact same amount of time to publish. But, well, actually, the bad ones might even take longer. And so you gotta not lose sight, as you learn this causal inference stuff, of just choosing the good questions. All right. And I know there's subjectivity to that. There is subjectivity to that. But I'm even saying, go back into yourself and remember why you got in this in the first place. Nobody got into this job to look at instruments. Okay. Yeah, I know. Youngmin said, the more I reflect on instrumental variables, the more impressive the method feels. It's very cool. Really, I completely agree. I completely agree. The more you, and I think that feeling really does start to, the deeper you go on all of these methods, and econometrics more generally, but this being the design methods, the more all of them, as they reveal themselves to you and they kind of blossom in front of you, you really do find them beautiful. They are very elegant. They are very beautiful. They are surprisingly smart. And, you can't help but respect the people that came up with them and for the advances that they did and how we all kind of benefit from it. And so I feel the exact same way. And it really never has ever faded for me. I think one of the things that I am very grateful for is that I'm not better at this. I actually was thinking about this the other day. Someone came and they, came to Baylor, a job market candidate came to Baylor recently, and he was asking me, well, how did you go from being an English major? I don't know if I told you all that. I was a literature major. I didn't have any math or stats or even any economics in college. I really was obsessed with reading books, reading poetry, and trying to become a professional poet. That was my real career aspiration. And I won all the awards that you could win for poetry at my university, and even had a national, got the Ruth Lilly Fellowship, the Ruth Lilly nomination, which is national, very competitive award that if I had won, which I am grateful I didn't win, but if I had won, they would have paid for a scholarship for me to get a master's of fine arts. And I only got into economics because in my literature program, this is what a lot of people don't know, but like in literature, it's predominantly the hermeneutic that you use to study the text is what's called Marxist critical theory. So we would study all this Marxism. It wasn't actually Marx, though. That would have been actually interesting, but it wasn't actually Karl Marx. But, it was kind of embedded in all this economic stuff. And so I kind of was reading more broadly in economics and just not the academic economics. And so when I read Gary Becker's Nobel Prize speech, which I think I mentioned on the first day, I just was blown away. And I wanted to be an economist. And then I took a couple of calculus classes in night school, and I took this principles of microeconomics class in night school. And I only applied to two schools and got into both of them with funding. And I was like, didn't really know what I was doing. If I was better, I think, in math and stats, but I wouldn't have to work so hard at understanding each paper. And I don't think I would be constantly trying to explain this material to myself. And what has been really rewarding is that because it is so hard for me, because econometrics, and even though it was my field, and even though I'm an applied microeconomist, every single paper I have to spend a long time really dissecting it, really taking it apart, going through every proof, going through every theorem, and that's not my comparative advantage, but I know you can't do anything unless you do that, and going through simulations and all this stuff. If it was easier, I'm not positive that I would devote myself to it. And I'm also not positive that that the beauty of it would reveal itself in the same way, because so many beautiful things, you have to pay for them. The really beautiful things in life are very, very costly. And so I've been really appreciative. I've been really genuinely appreciative that it's actually very, I have horrible sleep problems. Miguel asked, how many hours a day do I sleep? I have horrible sleep problems. And in fact, I was debating if I should even tell you all this. I thought might be oversharing. I might have had the worst sleep of my life night last night. I had nightmares all night, and intense stress induced nightmares. And they went on and on and on. And it was like brutal. And that might have been, I tried to go to bed early to because I wasn't feeling well, but I have horrible sleep problems and I can't easily fix them. And it's got, I'm trying stuff. Anyway, so all that to say, like Gene said, it is beautiful. And, if you ever find econometrics hard, the thing you should remember is you're not alone in it being hard. It is hard, but it is beautiful, and running marathons is hard and they're really beautiful, and raising a family is very hard and it's really beautiful. And so there's a lot of things that are like that, but anybody can learn it. Anybody can learn it. In fact, I would actually argue that it's the easier thing to learn. Econometrics has a lot of returns to experience associated with it. Every single paper, if you just approach every single paper as this is the opportunity for me to learn thing, this thing, okay, as opposed to I have to learn all of it. You just approach it like that, you'll learn. But I think that microeconomic theory or macroeconomic theory or theories in general, those things are much harder. Those things are much harder. There's a lot about that I don't think quite has the same returns to experience. So that's the great thing. I mean, I think actually the fact that all the fields have shifted so profoundly to applied empirical work, partly driven by all these computers being so amazing and so cheap, and all these data sets just swimming in them, has been really good for all of us, because it's put us on a path where we can get into returns to experience, meaning practice improves it. Practice is improves it. Thank you, Abjit. That's really nice. I'm glad. I thought that if we stuck with that I actually have found it to be a little bit insecure on my part. Should I go into so much depth like I do on this unconfoundedness and this potential outcomes? Because I have this is the thing I was kind of saying. I'm sorry, I'm rambling. I'll finish in just a second. But I have really good friends. Pedro Santana is one of my best friends. And he does workshops too. He's a brilliant econometrician. He's one of the most talented young econometricians. He has a photographic memory. He reads these econometrics articles at night and he never forgets them. He reads them before bedtime, and he never forgets them. And the fact I have to, so it's like, but here's the deal. He can go much faster than me. But all I ever think is that if I go faster, we won't learn anything. If we don't go through these spreadsheets and we don't go through these simulations, I don't think I'm good enough to do what Pedro does. So I have to go slower. But like I have to teach at Texas A&M, which is a university, and for those not in the United States, Texas A&M is it's not the state flagship school, but it's a very good university in Texas, probably arguably just as good as University of Texas. I have to teach their PhD econometrics class later in the semester. And all I want to do is do what we've been doing, but all I keep thinking is I got to go faster. And so I'm very torn, if I'm doing it right, but I really appreciate you saying that. I don't know what that Ronald's comment means, but I'm going to ask him offline what it means. So here we go. Let's get into this. All right. And let's go where we're going next. All right. So we did two-stage. Here's what we did. We did walled estimator, which helps us remember that IV is truly simple. It is very, very simple. It is a ratio of two regression coefficients. It's a ratio, and even more than that. If you're like, well, what's two regression coefficients? Well, even more basic than that, it's the ratio of two covariances. It's like the ratio of a correlation between the outcome and the instrument divided by the treatment variable and the instrument. And something about that, we went through it so slow, something about that just deletes a bunch of these biases so long as this DAG structure is true. Okay. If this DAG structure is true, then that ratio that ends up getting deleted. You take the ratio of this over this, and it just isolates the causal effect. And you could say the causal effect if you assume constant treatment effects, because if me and Miguel both get a 5% return to go into college, and so does everybody else, it doesn't matter which subpopulation you're identifying the effect for, because it's identical to everybody. The internal validity and the external validity is identical. We're going to learn later, though, that if the treatment effects differ by person, then we're going to see that this here, that this ratio still will identify an average causal effect, but it will be a little bit more subtle than we're saying. Okay. So now what we're going to do is so here, all right. So we look at this DAG structure again. Look at this DAG structure. Okay. A lot of what we've been doing, I think a way of summarizing a little bit about what we've been doing is I was really emphasizing this strangeness principle, right? Which is if Sunday candy is independent of you and Sunday candy is does not directly cause hell, then when someone reports the reduced form, i.e. the simple correlation between the instrument and the outcome, they are puzzled by even the existence of that correlation, because it doesn't seem to make sense to them without knowing the treatment. All right. So without knowing the treatment. So we said, like, what we said was the strangeness principle. And the strangeness principle is my phrase for talking about something more technical, right? First, it was covariance ZU equals 0, which we had kind of like subsumed into confounder and the error term, but we'll just kind of say right now, covariance ZU equals 0. But the jargon of instrumental variables calls that independence assumption, that the independent assumption would literally be this. It'd be, the independent assumption would be ZU, and that's called independence. And it implies that 0 covariance, all right? But the jargon of instrumental variables calls that independent assumption exclusion restriction. And that's what you'll sometimes hear. There's another phrase that Angrist and them like to use, and I'm drawing a blank. I dislike it so much that I like refuse to learn it. And it's not the word relevance. Somebody might know, Miguel or somebody, y'all might know what it's called, but it's not called relevance. It's called something else. So the exclusion restriction. And that's what I call it. The exclusion restriction implies the exclusion restriction requires two things. Number one, Z U, okay, independence. And then two, Z cannot directly cause the outcome. All right, cannot directly cause the outcome. And that's called the exclusion restriction. But there is a second historically important assumption in IV under constant treatment effects that is also just as important. And it is the strength of the first stage association between the instrument and the treatment. You need something called, and it's called non-zero first stage. And that's the one that Ronald offered an exclusion violation, which is the candy would be would bring in obese people, and then they would engage in gluttony, and that would directly cause hell in the old 7 vices of the old medieval churches, and that would be a violation of exclusion. All right, that would be a violation. That's very, very good. I like that. And that's kind of, actually, and Ronald saying that, I don't know if y'all can all see what Ronald said. Ronald saying that. This is actually, and I think this is interesting that Ronald did this. One of the things that starts to happen, to kind of go on what Ji Young had said, one of the things that starts to happen as your intuition, let's call it that, your intuition of instrumental variables deepens. You almost can't help but do it, is you start trying to think of, you start trying to think of this. You start saying, well, why might the instrument cause the outcome? Or you'll say this, you'll say, how might the instrument be correlated with the confounder? And, smart people, yeah, I think non-zero first stage is relevance, but I can't quite remember because I don't use those phrases. But this is like, this is the value, honestly, of the DAG, is that the DAG tells you the two things you got to be worried about. Tells you what the two things you got to be worried about when you're talking about exclusion. What would make Sunday candy or the instrument associated with the confounders? And smart people with this DAG, smart people can start running through those things. And then secondly, they start thinking, well, what would make the instrument directly cause the outcome? There's lots of ways that you can tell those stories. What I always try to say to people, though, is that, if they're not plausible stories, they're just kind of, and I'm not saying Ronald's is very helpful because he's being funny, but like, this is the thing is like, if you present an instrumental variables paper to a room of informed people, what they will do is interrupt you, and they will just assert a story that they have where the instrument is associated with a confounder or the instrument directly causes the outcome, they will assert it and you have got to be ready for it. You can't be defensive. You cannot be defensive. You cannot reject it because the problem is exclusion is not testable. Exclusion is not testable except under very, unique assumption-laden situations where those assumptions end up not being testable. All right. Like, when you have multiple instruments and you assume constant treatment effects, then you can do it, but you can't test constant treatment effects. So it's like all these kinds of things. Exactly. Akash says, just to clarify, yeah, there's like these rainfall criticisms. Oh, interesting. Okay, there's some interesting comments that are coming up. So this is, I think, the comments that came up yesterday, which was, the overall reaction, the overall reaction to IV is something to be kind of cognizant of. I would probably not say what those advisors say, though. I would probably say, what I would say is do not go on the market with bad instruments. Do not go on the market with implausible instruments. Well, I mean, I would say this, though. I mean, here's the thing. I just had this Journal of Human Resources, Cunningham. I had this good paper published. If I can pull it up. And, but the thing is, I have literally, in this study, I have actual coin flips that are coming from the random assignment of clinicians at booking. Okay. Now the paper, well, actually, you know what? We never sent it anywhere else. So who knows if it could have gone higher, but JHR is, to me, a very good journal. And so, the thing I would just kind of point out is that you don't want to go on the market with bad instruments, because if people can poke holes in it, they're gonna. Okay. There's almost like an efficient market for finding the problems in bad instruments. I mean, they're going to find it. You're not going to get away with it. So then Ari already says it's always important to discuss. Yeah, it is. It is. But so what you've got to do, in my opinion, is you cannot be the people in the audience cannot be the first ones to bring up these problems. Absolutely not. You cannot go in to so there's this funny line from Ted Lasso season 2 where someone made up a title of a fake Brene Brown book, and it said, come to the arena, but bring a knife. And that's how you have to approach these IV papers. Probably no other study is it as high risk, high reward as IV? Yeah, but it's not like, Ron, it's not like you could say, in my particular situation, is that going on? You might find, and the thing is, candy and obesity, candy. So that might help justify, right? So that might help give somebody support, but like you could not respond to that point, okay, and say, well, I do a test and I reject it. You can't do that. In that sense, it's not like testable the way that this next thing is testable. So anyway, point is, all the point I'm saying here is that IV is high risk, high reward. Okay. Because routinely, let's look back at this picture. 35% of papers published in the top economics journals, which are career making, to be completely honest, a top economics journal I've made this claim before, and this is probably an understatement, but a top publication in economics, the presently discounted value of it on your income, I mean, it is in the 6 figures, if not the 7 figures. It can get you tenure. It can get you a better job. It can get you a raise. It can have people paying attention to you. It has a huge effect. It had my top 5 had a massive change in my career. And so getting this out, getting it up there is very, very important. And whether or not you like it or not, you know, you cannot in 2024 do studies that are lazy on causal inference. They will not get into top journals. And the problem with the problem is not just, and the thing I'm not trying to make that is what I just said is very Machiavellian. Okay. I'm just kind of stating the facts. I'm not saying anything normative. I'm not saying good or bad, because when you're sort of obsessed with journal quality, it is genuinely soul destroying too. So you have to kind of approach this stuff a little bit carefully, but publishing well has many, many upsides. One is salary. Another is that people read the papers when they are published in higher quality journals. And it is very demoralizing to spend years and years of your life on a paper that nobody reads. It hurts the soul, you know, because unless you're just purely a self-expressive person. But the thing I would say is that what doesn't matter, I would say lazy causal inference is where someone is not thoughtful about the assumptions required for that methodology and is not careful about whether or not it is plausible with their data. Okay, let me show you this quote. Let me show you something real quick. Oh shoot, hold on. Let me just get into it here. There's this incredible quote by let's see, Dark. Here we go. Listen to this. 34 seconds. Hold on. Hold on 1 second. So let me, this is an interview I did with Orly Ashenfelter, who was really actually probably the one that is ultimately responsible for the causal inference revolution in economics, specifically this design-based. He was David Card's advisor, who won the Nobel Prize. He was Josh Angrist, and was also Josh Angrist's advisor. He's Bob Lalone's advisor. He was like Janet Curry's advisor, or Janet Curry was a Card's student, but like Oaxa, all this stuff came out of Orly running the Princeton Industrial Relations section. Listen to what he says instrumental variables was like when he was in the 70s and the early 80s. Listen to what he said the papers were like.
So it was a very hotbed place, but let's also remember we were picking low-lying fruit in a way. I mean, I still remember people publishing papers where they used instrumental variables and didn't tell you what the instruments were.
Oh, wow.
Quite common.
Wow. Yeah.
Somehow it was like magic.
The good old days.
Yeah. Yeah, instrumental variables and it's magic, right? That's actually the problem. You know? So we no longer have to worry about endogeneity.
Yeah.
So there was low-lying fruit, the standards in the
So like that would be an example of lazy IV, where you just kind of treat models, all right, as like sniper rifle bullets, and you're just kind of like, well, the model solves the endogeneity, as opposed to understanding the treatment assignment mechanism. Okay, the model does not solve this stuff. The model is not what makes something causal. Okay, the model is only causal if the underlying assumptions of the model are plausible in your data set. That's what makes it work. There's nothing magical about econometrics. That's why econometrics is like, the econometrics textbooks are like 10,000 pages long. You know, they're like gigantic. Why? Because you do this one in this situation. You do that one in that situation. You do this one in that situation. You do this one in that situation. You have to figure out if you believe this assumption's true. And like the empirical crisis in labor in macro in the 70s was, I wouldn't say it was late. I mean, you know, it wasn't exactly, it's not really fair, you know, to say, well, they were really stupid in like the 1910s, because look at the stupid airplanes they were using. They could barely get off the ground. All this stuff kind of builds on top of each other, even the bad work, or, you know, so-called bad work. I have this quote from my colleague, Jim West. He said this one day in a faculty meeting. He said, pioneers take arrows in the back. Like the guys that go first, the men and women that go first in, you know, new areas are always the ones that the people later just tear apart, right? But if, you know, nobody can tell that like they're chopping through all this jungle that allows the next people to go forward, you know? And so all I'm saying is that you can't go about causal inference of just being like, I just did this and I don't know why I did it. And I don't understand it because, you know, but like, I don't deeply understand it, but that's all I mean. Okay. But we need also, if we go back to this, okay, in order to do the walled estimator, all right, in order to do the walled estimator, we have to divide by the covariance. We take the covariance of the reduced form right here, take the covariance of the reduced form, calculate it, which you can do with the regression, divided by the covariance of the first stage, which you can do with the regression, which you can also do with two-stage least squares, because walled is two-stage least squares without covariance, okay, in a binary instrument, and a, you know, a binary instrument and you don't even, yeah, it's just binary instrument. So they're the same thing numerically, they're identical, right? And that's what we said, which means that cannot be, quote, zero. It's a little bit different than that because it'll never be zero, but it cannot be statistically weak. All right. And think of it metaphorically as like you can't divide by a zero. All right. That's the basic idea. You can't divide by a zero. All right. So we're going to look at dividing by a zero. It's called weak instruments. All right. And this is a paper by Isaiah Andrews, James Stock, who was a very important, I mean, he's alive, obviously still, but he was a very important econometrician. When I mentioned that Bruce Hansen, who I interviewed on Friday, had said that there were all these like pioneers, and it was like Whitney Newey and like Donald Andrews and Peter Phillips and all these guys that kind of like built some new architecture, which I got to re-listen to the interview again. I did not know what he was talking about, but like they did something. And if you were close to the source as they were doing it, which Bruce Hansen was, because he was a Peter Phillips student working on time series stuff at Yale in the early 80s, I think it was. Late 80s. Something like that. He Stock and Watson. Exactly. Stock and Watson. He's made major contributions to IV. He said Jim Stock was one of these people that just like revolutionized econometrics, or like part of this revolution of econometrics, which Shrey O'Shea, I think it was you, Shrey O'Shea, that was talking, or somebody was talking, maybe it was Nita, was talking about what felt like feelings that things had become obsolete with their training in the 90s and so it's like, so some of this is like general trends. Anyway, they have this paper, and this is Sophie's son of Son and Abraham, the diff and diff paper that has been very influential. This is what they say in a paper they wrote. They say, in instrumental variables regression, the instruments are called weak if their correlation with the endogenous regressors, i.e. the treatment variable, conditional on any controls, is close to zero. That is called weak. And we've got to figure out, well, what's the big deal? What exactly? It's like I said, it's kind of was metaphorical. It's like you can't divide by a zero, right? But that's not like, but it's never going to be exactly zero in a finite sample. So like what exactly is going on? All right. And that's what we want to look at now. And to look at it, what we're going to do is we're going to go back over this Angrist and Kruger paper. And I got a lot of really good. Yes, there is, Ligia. That's what we're going to look at, is there is a threshold. There is a threshold. And just as exclusion, as Ronald was kind of like telling a story where exclusion could fail in our Sunday Candy Hell example, where the arrows go directly from the instrument to the outcome, or they're correlated with the confounder. That's like a different criticism of an IV paper. All right. No, it's not going to be the Sargent test. It's not going to be the Sargent test. It's going to be a particular kind of F statistic and something called an Anderson-Rubin confidence interval. But talking about exclusion violations is almost like a different, it's like the left side of the brain. Okay, it's not testable directly. Ronald kind of said I could bring up evidence supporting my story, and that's true. But like, that might not hold in this data set. That could hold in other data sets or more generally, but it might not hold in this particular data set. Okay. But it's not testable. Exclusion is not directly testable, except under very, very specific situations that are not generally applicable. First stage weak instruments is actually unique because it is directly testable. Ronald could say, I don't believe you have a strong enough instrument. And you could go, I do. And here's the table that shows it. And Ronald would have to go, oh, okay, yeah, you do. I still don't believe exclusion, but you're right. You showed me that you do. So what we're going to do is we're going to say, all right, well, what happens to two-stage least squares? What happens to two-stage least squares if you have a weak instrument? And to do it, we're going to go back over an old paper by Josh Angrist and Alan Kruger, who's no longer alive. He died in, I think, 2018. It was tragic, and he died, and he would have definitely won the Nobel Prize with Card, maybe even Card and Orley. But the way that the Nobel Prize is done is you cannot be dead. So it's not a posthumous prize, and you can only give it to 3 people. And so when Alan Kruger died, what looked like, my theory, what happened was they just decided to combine Angrist, Embens, and Card. And I think Orley got, well, who knows? I bet, they don't report, like the runner-ups. It's completely behind closed doors, and nobody knows how they like go about making this little Lego kind of thing where they kind of combine people. They combine a lot of people. Sometimes it's very weird the way the combinations are. You have to really, ask ChatGPT probably, like, why are these 2 people going together? I can't even understand it. And sometimes it's more logical. Anyway, Kruger died, and in the interview that I do with Josh Angrist, he talks a lot, and I do. Okay. So what I'm going to do is let's take a 15-minute break. But for those that want to stick around, let's listen to Josh, who wants to listen to Josh. Let's listen to Josh tell a story about IV. All right. I don't think it'll take 15 minutes, but he's going to tell in this story. All right. In this story, Josh Angrist, who won the Nobel Prize in 2018, he's going to tell something about how this paper that he wrote with Alan Kruger was essentially, it was discovered to have a major weak instrument problem. But it's kind of interesting because it really sort of tells a more personal story, which was they were pretty freaked out. Right. So we're going to listen to this. We'll come back in 15 minutes to the lecture.
Yeah. So there was some pushback. That's to say that. Yeah. Okay. I don't want to skip over Alan Kruger. I have here a question about him. So
Sure.
So what worked about that relationship for both of y'all? How is it different than how is it
Oh,
different?
hold on, I'm sorry.
And
My
how is it
bad, my
similar
bad.
to your work?
I didn't share the screen. All right, I thought was still doing it. My bad. Okay. Thank you.
Yeah. So there was some pushback, that's to say, yeah, okay. I don't want to skip over Alan Kruger. I have here a question about him. So what worked about that relationship for both of y'all? How is it different than how is it different and how is it similar to your work with Embens in terms of just the productivity of it?
Well, Alan and I did applied work together.
Right.
We also, hit it off fairly soon when he came to Princeton. Orly brought him. I don't think he was going to be given a fly out on the junior market. And then Orly's wife sat next to him on a plane.
I heard that.
Yeah, great story. And Jenna Ashenfelter knew enough about our world to know that Alan was worth talking to. And Orly followed up, and then Alan came to Harvard. I mean, came to Princeton.
Yeah.
And actually, Alan and I were friends, and we enjoyed working together. But we had a little bit of a competitive edge in our relationship because Alan was the Harvard guy and I was the Princeton guy.
Oh.
And I think at Princeton at that time, we thought, those Harvard guys are not very rigorous.
Oh.
And, they don't really know much econometrics the way we do.
Uh-huh.
But Alan, of course, was a gifted applied econometrician
Mm.
and very systematic thinker.
Mm-hmm.
And so we meshed very well. He had lots of ideas about how to look at empirical relationships. He was also a very good writer.
Mm.
And I learned a lot about writing papers from working with Alan.
Yeah.
Which is
Did he
something
think about
that
that?
Today emphasized,
What did he think about the work you were doing with Ruben and Emmons? I'm just curious.
Alan was very interested in it.
Uh-huh.
And, he was, Alan and I ended up working with Hito on the many weak instruments problem.
Yeah, right. Yeah.
And,
So he was very, yeah. I mean,
well, he was excited, we were excited by the quarter birth discovery that was an instrument for schooling, which, for labor economists, I'm sure you'll appreciate, that's like the holy grail.
yeah, yeah.
That's our big causal question. Do people who are more educated earn more?
Right.
Because of their schooling, or is it just that the people who are gonna be doing well in the economy anyway get more schooling because they come from better family backgrounds or more well-off families?
Yeah.
And Alan and I felt like we had a solution to that problem. And we were super excited about that. It was a very exciting time.
Yeah.
We had sort of stumbled on it.
How'd y'all find that? You didn't just reason it, reason it out from just kind of reading the compulsory schooling stuff?
No.
He's talking now about the paper that we're about to discuss, okay? Quarter of birth, compulsory schooling. So now start listening.
It was a byproduct of work that we were doing on World War II veterans.
Oh, really?
So Alan came to Princeton, my thesis was kicking around in a working paper, I think.
Mm-hmm.
Already I had some results by the time Alan came.
Mm-hmm.
And, Alan observed at some point that everybody thinks that World War II veterans benefited from their service. And it's true that if you take the relevant cohorts of men born in the 1920s, men who served in World War II earn more than men who don't.
Mm-hmm.
And, you could explain that my Vietnam thing is negative, but maybe the World War II guys benefited because, the GI Bill is such a big deal and so on. So there's, it could be that it's just a different thing.
Yeah.
Later, I learned that that's probably not very likely, that there was a substantial GI Bill in Vietnam, in the Vietnam cohort as well. But anyway, and then of course, there's a strong case for believing World War II effects are contaminated by selection bias. The World War II veterans, for example, live longer than non-veterans the same age. That's a classic example of selection bias. Because the process that determines who's a veteran at that time is basically screening out people with health problems.
Oh, right.
And very low test scores.
Of course.
So, Alan and I were looking for an instrument for World War II veteran status.
Yeah.
around 1991. And we started, so we did approach the problem like I described to you. We were reading the selective service publications, the selective service system that's responsible for conscription. And we were really reading all their old reports and everything. And we discovered that there was a kind of a chronological birthday-based conscription thing. So it wasn't the lottery, but it was in order of your day of birth. And there was a kind of a first stage for that. It wasn't great, but it wasn't nothing. But
Yeah.
we started to look at what else is correlated with your quarter birth. We saw that there were these striking up and down schooling effects that didn't seem to have anything to do with, you know, veteran status.
Yeah.
It was just a very different pattern.
Yeah. The
And-
same graph that goes in the paper, with the dots?
Yeah, we had some version of that.
Yeah.
And we just puzzled on that for a while, and eventually it occurred to us that this whole compulsory schooling thing, and you know, we collected a lot of evidence in support of that.
Yeah.
So the interesting thing is that World War II paper was published 3 years after the AK-91 paper. So we had problems publishing the World War II paper, but maybe we should have, because by then we had shown that it wasn't a very good instrument for veteran status because it was correlated with schooling.
Right. Yes. Yeah. Of course.
But anyway, that was a lot of fun. Those were joyful times, you know, working with Alan. His loss is a great tragedy.
Yeah.
You know, I remember those days quite vividly.
Mhm.
And we felt like we were onto something. You know, not only was that an important application, but we did have sort of an MO. We had a way of approaching empirical problems. And then we had a way of doing things with two-stage least squares, which maybe, you know, some of that didn't turn out to be a great idea. Lots and lots of instruments didn't turn out to be a great idea. So John Bound and Bound Jager Baker showed that in 95. That was kicking around in 93. Alan and I lost a lot of sleep about that, the weak instruments problem. But then that was very fruitful as well.
Yeah. What can you elaborate on that? That's the kind of thing I think that a lot of us sort of worry about a little bit is anything that comes out. Well, some people do. You know, I know that I have something that might come after me and criticize, and I might not be that. Well, maybe.
Well, it's not fun when somebody takes apart your work and finds a problem with it.
Yeah.
You know, the first time that happened to me was when I met Paul Becker. That's Becker, Bekker.
Yeah.
In a bar, a pub, I guess you'd call it, in Amsterdam. It was like my first talk in Europe since I had been on the RES tour. And Geert Ritter had invited me to Amsterdam, and Becker came up to me in this after seminar I had given, I think, one of the versions of the late paper. And he said, you know, your draft lottery thing, that AER paper, that's all fucked up. And I said, well, who are you? You know? And he goes on to tell me that I'm using too many instruments and the thing is badly biased and et cetera, et cetera. And I was kind of dismissive at the time. But of course, he turned out to be right. And he has a very important paper explaining all this, which is published before BJB. 94. But Becker's paper is motivated by my draft lottery paper, but it's not really an empirical paper, and it's, you know, not something that's easy to read for people who aren't schooled in the relevant theory. But he turned out to be absolutely right in general, though my draft lottery paper was a 2-sample problem, so it doesn't have the many weak bias. But I just got lucky there.
Yeah.
It could have, and you know, today I would say, well, also the just identified estimates are the same, and they're not biased. They're not
Right.
But you know, so that's very stressful for a scholar when somebody comes along and says your work is all fucked up.
Right.
And you've made a mistake or you've failed to notice something.
Yeah.
When I, you know, now I have the wisdom of experience, and I could say, well, in many ways, that's the best thing that can happen to you, because it means that somebody took your work seriously enough.
Yeah.
that you were worthy of investigation. You know, most papers are not worthy of
Right.
investigating. It's sort of clear that we shouldn't take the empirical results too seriously because the analysis isn't convincing, or the person doing it has not taken the trouble to
Yeah.
report them in a credible way.
Right. Right.
And so when Becker or somebody like that comes along, yeah, it's stressful for the receiver, but it is ultimately a compliment. You know, looking back on the many week thing, that was tough. Alan and I were losing sleep over that. Alan had suggested to John Bound, who had been his classmate at Harvard, that John do this thing where he just draw the instruments randomly and see what you get if you estimate our models as if, you know, they were real. Well, you do get something that looks a lot like what we got when the models are the 180 instrument model.
Right. Right.
Well, that was terrifying.
Mm.
You know, it meant that we had, you know, we were sort of felt like, oh my God, we had fooled ourselves and we had fooled the world with this paper that got a lot of attention.
Yeah.
You know, Jacob Mincer was super excited about our paper. Gary Becker was super excited about our paper. And,
oh man.
you know, the big substantive finding was that OLS and two-stage squares.
Right. Right. Oh, I bet they were. I bet they were.
So, but then Alan and I was back in Israel at the time. So that was inhibiting sort of interacting on the problem. As it happens, that summer, I was on reserve duty and I was doubly miserable because there was limited attention I could give to the problem being isolated out in this desert outpost. The upshot of it is we started working on it. We came up with the split sample IV, and then we started working with Hito, and we came up with lots of solutions to the many week problem.
Right.
And I remember a very gratifying summer institute at the NBR where a lot of that work was presented. And I felt very good about that. I thought, you know, it's real science that we're doing here.
Yeah. Yeah. That kind of reframing of it, that's a useful skill in life in general of kind of getting a hold of those things that hijack your interpretation of these events that are happening. It is scary to admit. It's easy to go into stories where you question who you are or you feel bad about yourself.
But you have to remember, of course, everybody makes mistakes, and scientists and researchers, you know, there's so much detail and so much work involved in any given project that you probably made some mistakes.
Yeah. I only have a couple of minutes.
Isn't that great? I love that. I love these. If you have a chance to listen to my interviews with Hito and with Josh and with Card, I'll be completely honest. I think they're the best interviews anybody has done, because for some reason they kind of open up a little bit more about the personal side of the work. And they'll get into these, like, you know, the origin story. It kind of feels like, you know, Spider-Man or Superman or Batman kind of telling, you know, how all this stuff emerged. And it's really special. And that interview right there, you know, what he's discussing is this paper, this weak instrument paper, or what he keeps calling the mini weak. It's classic paper. And it was written with Alan Kruger. And you know, what's interesting is if you listen to Josh's interview where he discusses Alan Kruger, and then you listen to David Card's interview, because Card was also a co-author of Kruger's in like a famous paper. And then you listen to Steve Pischke of Angrist and Pischke, Mostly Harmless Econometrics, and you listen to my interview with Pischke, who criticized a paper with John DiNardo. They criticized a paper by Alan Kruger, and they were his students at Princeton. If you listen to all three of them, you just kind of get the sense. Yeah. If you Google it, not Becker 1994, Akish, you can find it. I might even have it in the readings. If you listen to it, you kind of get the sense, to be honest, that Kruger's most famous work, he took a real beating for it. You know, he's really well known for Angerson Kruger, Angerson Kruger, 91. And why is this paper famous? Because it helped us understand the weak instrument problem. But what does that mean? People realized the paper was flawed. He's really well known for the Carden-Kruger 1995 minimum wage paper that used diff and diff. A lot of the things about that paper ended up being, I think, kind of traumatizing because that paper brought so much criticism by the non-labor economists. The labor economists, Orley said, found it to be fairly acceptable. But I mean, you got James Buchanan writing an article for the opinion piece in the Wall Street Journal, basically saying anybody that believed that paper was quote unquote a camp following whore. Says that in the Wall Street Journal. Card said people openly accused them of fraud in that paper. Well, really, really famous people. And I mean, by that time, Buchanan was a Nobel laureate. And at that time too, Kruger was was working in the Treasury, or it was the Department of Labor, one of the two. He was in government, and a senator from either New Jersey or Pennsylvania basically managed to get him audited, his taxes audited, for like political motivation because of the paper. And then third, that DiNardo Pischke, I asked Pischke a question at the end. I was like, what do you wish you could, I didn't say, what do you wish you could have done differently? I just said, what do you wish, if you could go back in time, and talk to your young self, what would you say? And I had no idea what he was going to say. And Pischke said, it was actually kind of sad. He said, I wish that we had sent our paper to Kruger, because they basically showed that paper was flawed. And they never sent it to him, and that was their professor, And Pischke kind of had some regrets and so, see, Kruger committed suicide in 2018. So it's kind of got this, like, not that it had anything to do with that stuff. Okay. Not that it had anything to do with that stuff, but it's like you listen to it and, Anger's saying me and Kruger had sleepless nights, and Angrist was in Israel because he was at Hebrew University, and he was, I believe, maybe even fulfilling his citizenship requirement to serve in the military. I'm not positive, but he's one of the two. He says we had sleepless nights, and they're on other sides of the world, so they can't even communicate. And there's, it's 91 or whatever, and so maybe they're talking about email, but they can't easily communicate. There's no Zoom. And I asked Card, Card said that him and Kruger weren't friends. They just were there. He said they weren't friends. They were just good co-authors, which is kind of almost makes me cry just saying it. It's like friendship in the co-authoring and no friendship in the co-authoring is so different for me personally, because the projects are just so grueling. They're so grueling, It's like not having a friend to go through it with you is just so hard, It's just so hard. And I've had it only happen a couple of times, I would say, but I almost require it now. But everybody's different. That's the thing too. Everybody's personality is different. Not everybody is as sensitive as I am. I get super sensitive. I have hypersensitivity. And it's not healthy. It's not healthy. But when I hear these stories about Kruger, my heart kind of breaks, and I just always wish, and I get storytelling. Anyway, here's the deal. So this is this paper, all right? This is this famous paper. And Angerst and Kruger do it, all right? And so it's brings sharp focus into this weak instrument problem. But it is a wonderful paper. It is a wonderful paper. And just like Angerst said, they not only feel that they have found evidence, he said the Holy Grail, for those of you who are not in econ, finding causal evidence that schooling causes, not just correlated, but causes earnings to go up, given the whole tradition of economics. If you can kind of just like step back, what is economics about? It's about inequality. Why? Adam Smith is studying the wealth of nations and the causes of it. Why? Because humans have lived in dire poverty for basically the full history of humanity's existence, except for the tiniest little sliver at the very, very end of like history where they've been just astronomically wealthy. And when you have this growth in income, and you have this growth in income, and in capitalist systems, you use that income to buy our goods and services. Those goods and services meaning clothing, food, housing, all the basic needs of life. And you start to kind of try to understand that there's still all this inequality around the world and within countries. You know, you start to realize if there are poverty programs that can cause really large increases in incomes, then it's like people use those incomes to do what? To like feed their life, to make their lives better as they decided. And we have never had that opportunity for all of history. All of history, human beings were basically living at a calorie budget constraint. I mean, they were lucky to have enough food, okay, on a day-to-day basis. And it was, you know, blood, sweat, and tears. And so to find this evidence of a causal effect of a program like education actually causing wages to rise, you know, it's huge. It's a big, big deal. It's a big, big deal from a policy perspective. It's a big, big deal from a science perspective. It confirmed things that Gary Becker had argued since the 50s, which was education raises the productivity of workers. And in these market economies, that increase in productivity raises their wages. It's like, it just was like a massive thing. Okay. And since it's at the source of this like very credible instrument, it again kind of had this like appeal where people were like, man, this is dead on an accurate way to go about stuff. And it turns out it's flawed. So in practice, though, it is very difficult to find convincing instruments precisely because of the kind of reasoning that Ronald was doing before, which was it is very, very hard. And I said lazy causal inference. It is very easy to run IV. It is very hard to have a valid instrument. That is not the same thing, okay? Because usually potential instruments don't satisfy the exclusion restriction. But sometimes papers will have instruments that plausibly do satisfy the exclusion restriction and yet still be problematic because they fail on the strong instrument issue. Okay, so we're going to look at this paper that was really valuable for the exclusion restriction, but ended up being kind of exposed because of its problem with the weak instrument. So they're interested in estimating the effect of schooling on earnings, and they instrument for it with which quarter, meaning there's January, February, March, first quarter, April, May, June, second quarter, July, August, September, third quarter, October, November, December, fourth quarter. All right. And they find that if you instrument for schooling with which quarter of the year you were born, that, you know, they recover the effect of education on earnings. And if you think back to that strangeness principle, okay, you can see why it's kind of got like a little bit harder. It's a little bit strange, right? If someone was to report that there is a correlation between how much money you make and whether or not you were born in January or December, okay, it seems odd because there's nothing about January and December of the same year, okay, of the same year. There's nothing about January and December that should, if you told this to Gary Becker, who's an expert on education, he would go, well, that doesn't fit my model. That doesn't fit my model. There's nothing about December versus January that have anything to do with worker productivity. And there's nothing about firms where they're going to give you a raise because you're born in December and not January, right? So it's like all this stuff, okay? So here's what they sort of had found, and Angus kind of mentioned it. He said that he had been doing his job market paper that basically got him a job at Harvard was on the Vietnam War, and it was estimating the effect of military service on career earnings, using as an instrument your draft number, which was random. And he had these like physically random instruments, and it was like a big deal. It led to the pioneering work that he does with Embens. And in the process of doing that project, he had kind of learned, he was kind of doing other stuff. And basically in the end, they find this thing, which is that school districts require in the United States to have turned age 6 by January 1st of the year in which they enter school. And there was this compulsory schooling law throughout the United States, which was you couldn't drop out of school until you were 16. So you've got people starting school at different ages, but they all get to drop at the same age. It looks like this, okay? So you got basically people born in December that are effectively able to drop. They're able to drop earlier by that much than if you were born in January. So if you were born in January, you start school, you start age 16 a little bit later. And so by the time you're hitting age 16, you've not got as much school if you drop out. Now, it's not much. See, and this is going to get into the weak instrument thing. It's not much. It's a little bitty bit. Okay, it's just a tiny little bit. But technically, you're essentially randomizing, potentially, schooling. At least that much. Okay, at least that much. So they thought about it. It was very clever. And you have to kind of think back to what Orley Ashenfelter said. Yeah, exactly. Maybe it was validity, actually, Miguel. Maybe it's validity and relevance, valid being the exclusion restriction. Maybe that's the word. But think back to what Orley Ashenfelter had said. Right? So this is like 1991. And Orley says, I still remember the day when people wouldn't even tell you what the instrument was. Okay. Yeah, exactly. So it changes, Nita, and there's all kinds of stuff about it. It's like a whole other literature about whether or not it really does validate, if it is valid now versus back then. So that's kind of thing. So here's the visuals, and I'm going to kind of allude to this later. You need good data visualization for IV because of the amount of scrutiny that those papers get. You have to lead almost. You cannot in these IV papers, you got to hear me. You cannot in this IV stuff that you do. You cannot in this IV papers just go to a table of coefficients because of the amount of scrutiny. So one of the ways that you really have got to appeal to the audience is up front, show that Wald estimator, show it. And I do not mean the actual statistics necessarily. Show them a picture of the correlation between the instrument and the outcome, quote, the reduced form, the numerator of the Wald. Show them a picture of the correlation between the instrument and the treatment, i.e. the first stage or the denominator. Show a good picture. Every project that uses IV, you guys have got to figure out a way to find a very compelling picture. And actually, since ChatGPT 4 is out, you ought to just tell ChatGPT 4, here's what I got to come up with. Cunningham says I got to come up with a fantastic picture. Here's my story. Here's my narrative. All right. And I've got a correlation. When I run a regression of the outcome onto the instrument, I find this thing, it's highly significant, but I cannot figure out a good picture. What do you think it should be? And ask ChatGPT 4 to do it. Or Gemini, the new Google one. So here's what they did. This is a classic and compelling, simple picture. All right. So first is they show the first stage. All right. They show the first stage. You can go in whatever order you want to do, but the first stage is what they show. And here's what they're showing. Okay. Here's what they're showing. For this is a 1930 birth year. All right. This is the year of birth. All right. Year of birth. And in 1930, try to ignore this like rising part. It doesn't matter. I mean, it does matter, but it takes me too long to explain it. Just look right now at the within birth cohort variation. Okay. So all of these are the 1930 cohort. They have to space it out. Right. So that was the part they had to figure out, you know, is you couldn't just show this on the 1930 plot because they'd all be sitting on top of each other. So they space it out. Okay. So if you're born in January, February, March, all right, you get this amount of schooling, 12.3 years of schooling. If you're born in April, May, June, you get a little bit more. April, May, June, July, August, September, a little bit more. July, August, September, October, November, December, you get more. Now look at this, all right? 4, 3, 4, 3. Now it gets a little bit weaker here, threes, but across the top, and it does get weaker over time. Now that's going to be part of this problem. But it's like sometimes it's really strong. Sometimes it's really strong. And then you got in the bottom ones, 1, 1, 2, 1, 2, 1, 1. I don't know what that is. It looks like that's another 1. I don't know why that's missing. 1, 1, 2, 1. Then it gets weaker. Okay. But you do find this correlation between birth quarter and the amount of schooling that you got. And then he does the reduced form. Now, so many times, this is just a little aside, it's like I have this really strong opinion about this, but I don't really try to bring it up in a seminar when we have the job market candidates come out. I don't like to bring it up in a seminar because it's so, you know, like little bitty points, but people are not using enough of the shapes in their plots, and they're not using enough of like different shapes in the plots. What people do too much, in my opinion, is have lines with different colors. And, you know, people cannot tell the difference between those lines with colors. Some people are colorblind. And if they print the stuff out, they're going to be printing it out usually on a black and white printer. They're not going to be able to know. So you got to use these, you got to use symbols, in my opinion. So look at these symbols. Hollow lines at the top. See, these are log earnings, and log earnings don't have a lot of variation because log earnings have, by definition, less variation. So, so they put log earnings on, all right? And look, you can see because they've got the one black symbol is the one. Yeah, it's the one. Look, 1. It's always the black that appears to be at the bottom. Not always though. See how it's getting weaker? See that? Or this is the reduced form. This is the reduced form. All right. You know, small differences though in log points are large percentages. So that's the thing. You go from like 5.8 to 6.1. That's a big increase in percent. Right? It's a small on the log points, but differences in log points can be interpreted approximately as percentages. Not percentage point, but percentages. So this actually is not trivial, but visualizing it's a little bit harder. So you want to do it. So that's what I'm going to say at the end. When you're writing these IV papers, you got to have a killer graph figure of the first stage and the reduced form. even though you're not going to do the walled estimator. The walled estimator is what you got to visualize, not two-stage least squares, because there's too much machinery in two-stage least squares, and you're not going to make it compelling. All right. You're not going to make it compelling. So you got to figure it out. And it gets a little harder to figure it out when you got a binary instrument and a binary treatment, because those typically are more difficult to visualize. Even though, because you got 0, 1, you got 0, 1, it's like, it's kind of a little bit harder. You're going to have to think about it. All right. So there's no one right way to do it, but like there is a lot of bad ways to do it. Okay. If that makes any sense. There's a lot of bad ways to make figures, and there's no necessarily one right way. But this is the kind of thing I'd also like to say. Econometrics does not teach you how to make good pictures. The kinds of people that are good at making very good pictures are the same kind of people that like really know how to what kind of paint really goes with a room, and how a rug really like brings a room together. And they they have a visual mind, which is not the same thing that makes you do well on the econometrics prelim or the stats exams. Okay. But this is something you got to lean into. You got to lean into it and say, I actually do dress well. I'm very good. I'm very fashionable. That person has to be empowered to really think through this, so long as they understand causal inference. So when we showed this figure of reduced form, could it be confusing for folks to say that this shows you should put the year of birth in the earnings regression? No, because that's where what you've got to do, Akish, is you've got to kind of lean in on the front end and say, I'm going to be doing instrumental variables. That's what you don't put in an IV, you do not put, you don't put the instrument in the regression. Okay. You use the instrument to instrument for the treatment. So, you're not arguing here that you have an omitted variable bias problem. Okay. That's why you put covariates in, because you say I have an omitted variable bias problem. Instruments are not putting an instrument in a regression is not the source of the omitted variable bias problem. It's not putting the confounder in, and the instrument's not even correlated with the confounder. So it doesn't even solve anything. All right. You've got to be educating the reader. If you believe you are in an audience, okay, all of this actually, to kind of Akish's point, all of this is actually based on who is your audience. If your audience is a group of people that are very, very well informed about instrumental variables, they're going to understand that you don't put the instrument in the regression. But if you're speaking to a group of people who do not have nearly the level of literacy over IV that you do, then what you got to do is start with that. You got to put the DAG in. In econ, people don't need the DAG usually, but you might put it in anyway as a bullet to kind of reason out why you do it. But see, once you do this, you say, and that is why I am not putting the instrument in the regression, because see, the instrument doesn't explain the outcome. It's not helpful. You don't control for instruments. You use instruments, but you don't control for it. It's different, because this is not about unconfoundedness. All right. So let's remind ourselves the two-stage least squares model. All right. So you got a causal model here, Y, covariate, schooling, all right, error term. There should be an I there. First stage regression, okay, you've got schooling, covariate, instrument, psi, or eta, or whatever it is, and the reduced form, outcome, instrument, right? Keep these separate. The causal model is Y as it relates to schooling. The first stage, schooling as it relates to the instrument. Reduced form, outcome related to the instrument. The walled estimator can be considered a ratio of pi 2,1 and pi 1,1. Because remember, all that the walled estimator is a ratio of the correlation between the outcome and the instrument divided by the treatment and the instrument. And you could run a regression, and that would be like a partialed out. it'd be like a partialed out wald. Partialing out is language that comes from the Frisch-Wald level theorem. That would be like the effect of the instrument on the outcome controlling for X. So that all of the remaining variation is not including that. So that would be like pi 2, 1, having partialed out the effect of X on Y, and partialed out the effect of, and any correlation also between the two. All right, you can do that. That's the sample analog of the Wald estimator that adjusts for covariates, because the simple Wald estimator, remember, does not control for covariates, but you can do it. That's not what they do, though. All right, that's just kind of a heads up. So Angerson-Kruger instrument for schooling using two-stage least squares, which is like this. First stage, regress schooling onto dummy for, they have 3 dummies as opposed to 1. They can't really do the Wald estimator here, is the thing. When you have more than 1 instrument, you can't do this kind of Wald stuff. But the idea is that having established that Wald and two-stage least squares are the same thing, you can go into two-stage least squares and use multiple instruments. Okay, you can use covariates, you can use multiple instruments, all this stuff, and it still will hold. And you'll get consistent estimates of the treatment. That'll still be consistent even with multiple instruments, right? So you get here, schooling regressed onto the covariate and the instruments. Use these, let me put this in here. Use that coefficient to get a predicted schooling, which is what that is, in the second stage. And then you basically regress the outcome onto your covariates. I forgot all these I's. Onto the covariates and predicted schooling. Now, you're always going to have larger standard errors when you run IV, okay? Because IV does not have as much variation in your treatment variable, because you are removing variation. You're removing variation in the treatment. You're leaving it only with the predicted schooling, which will have less variation because you have deleted the problematic variation. You've deleted it by using the instrument, which means that this will always have, you know, smaller variance. Yeah, they have to be the same thing, Julietta. They got to be the same thing. No, this model should not be under identified, although I'm not positive what you mean by it. You'll be able to, but I'm not positive if I mean the same thing as you do. No, that's what instruments are doing. Instruments are net of the unknowns. All the unknowns are in here, are captured here. You have exogenous variation right now. You have exogenous. Oh yeah, you've got it over-identified. Right, exactly. You've got it over-identified. You've got exogenous, though, variation in the treatment. You do have a lot of unknowns, but they're all subsumed here. And the variation that you do have in schooling, so long as exclusion is satisfied, this is random. This is random right here. And that's kind of the power. All of those unknowns are independent of schooling. Predicted schooling, rather. Predicted schooling. So here, we're going to, the Sargan test, yeah, with over-identification, yes. Under constant treatment effects, Sargan will allow you to check that, Eduardo, but under heterogeneous treatment effects, all these exclusion tests are not valid. So, but that's historically, there's assumptions within the Sargan test that are not still testable. Can you explain the random part again? The random part means this. Randomness means that the variation in treatment is coming only from the instrument, not the confounder. It's coming from the instrument, and it's coming from the error term, an error term on this, okay? So you've got this like error term that is also determining, that's also determining church. So you've got with this treatment variable, what you've managed to do with instrumental variables, when you instrument and you have a valid instrument, you now have as good as random variation in treatment. Now, since it's only coming from Sunday Candy and it's only coming from the noise term and is independent, it's independent of, it's now the variation in church is exogenous. Yeah, that's right. That's right. You have to, Legia, I mean, I'd have to go through the proofs, but in order for two-stage least squares to be consistent, the model has to be the same in the first and the second stage. So you have to carry it down. It has to partial out both times. You have here, look, you've got here this determination of hell, and it's coming from church, and it's coming from the confounder, and it's coming from V, but this variation in church is none of the confounded part. Okay, it's none of the confounded part. You've netted it out. But see, the thing is, part of the variation in church was coming from the confounder, and you just removed variation. And one of the things that allows you to identify a parameter is variation. So if you reduce the variation in a variable, you'll always kind of blow up those standard errors. And so that's one of the things, actually, one of the things with IV is that by nature, mechanically speaking, by nature, it will have larger standard errors. Okay, it will have larger standard errors because you now have a variable that has less variation in it. So traditionally, Eduardo, they are. No longer is that really true. Angrist and Embens win the Nobel Prize for introducing heterogeneous treatment effects into instrumental variables. And I think it's no longer really probably true that people start with assuming homogeneous treatment effects. This world that we live in now is potential outcomes laden, and potential outcomes assumes unbounded theoretical, potentially heterogeneous treatment effects. So you should always be worried about heterogeneous treatment effects. But so like as a rule, if you're outside of econ, I think they're like probably, I did this Twitter poll one time, and or not really a poll, but I asked people, I was kind of curious because in epidemiology is one of these areas that, like economics, has kind of like fully embraced causal inference for a long, long time. And they have kind of a different approach, but like they've done it for a very long time. And it's kind of a mature area too. But I had this this thing that I had kind of started to notice. And I was like, I'm just curious if you make an assumption compared to OLS, usually compared to OLS, Shube, if you did the OLS model of Y onto the outcome controlling for X, the standard errors on OLS would typically be smaller because there's more variation in the data, and IV will typically raise it. But I asked these people, I said, do you typically assume homogeneous or heterogeneous treatment effects? And epidemiology, by and large, when they start, they assume homogeneous treatment effects, and economists basically never do. And I'm not really sure why that is, except that Angrist and Embens were economists, and that work really did drive this credibility revolution, and IV was really driving it too. So there's like different disciplines that do this, and so some of it is just, that's part of it, All right, so then they got this they got this table here quarter birth, strong predictor, total years of education. Okay. So they put this table in and they show in a regression, this F test is not what you think it is. So I'm just going to delete it. It's not the F test. It's the F test on like the entire model, not the excludability of the instrument. No, heterogeneous treatment effects is not heteroscedasticity. Heterogeneous treatment effects means, is it the case that some people have larger or higher or no or negative returns to education? They each have different causal effects at an individual level. It goes back to that potential outcomes that we did on the first day, where we allowed for not everybody had the same returns to the drug as everybody else. And that's heterogeneous treatment effects. Artie, should you explain the mechanics of randomness in IV? I personally believe that yes, you have to. I think that that's part of your job. That doesn't mean that you go on for pages and pages. The papers have to be readable, but I do think you do need to explain why it is that we should believe that excludability holds. That's the thing. You gotta do that. So here we have this regression of schooling onto the dummies for quarter of birth. And for the 1930-1939 cohort, the average schooling, 12.79. But if you're born in the first quarter compared to December, your years of schooling is 0.1 years smaller. And it gets, increasingly smaller as you get closer to December, and then it gets weak. Okay, I'm going to go a little faster. So then and so this is what I was saying, Shubhangi, OLS. I don't think so. I would, because you're not really, I wouldn't do it. No, I'm just saying it for your sake is, notice how, look how big that jump is. 161, it's like, here, let me, what is that? 0.0161 divided by 0.0003, 54 times larger standard error. Okay, 54 times larger standard error. Well, they're only using the variation in schooling that comes from which quarter of birth you're in and like what year of birth. That's it. So that means basically, Dong Lee, if you and I have the same year of birth and we're both born in January, we're going to have the exact same schooling, even though maybe we have different schooling. We're going to have the exact same predicted schooling. So like anybody for whom quarter of birth is the same and these other explanatory variables are the same is going to get the same predicted schooling. And so as opposed to what is in reality, much richer variation. So if you have less variation in a variable in a regression, you'll always get larger standard errors because, when you think about, your ability to identify an effect that's coming from variation, you need the variable to vary. So in the limit, you can't even identify, right? So they do it. And so watch what happens. They've got three instruments, all right? And you've got here 0.0711, and you've got this larger standard error. Now, it's still statistically significant if you could kind of imagine doing that, the T. It's big. It's 5, whatever, roughly 5 or whatever. So, it's highly significant, but it's not different from OLS. So it's like if you did 0.0, so let's see, like 1.96 times 0.0161. That's 0.03156. Let's see. 0.0891 minus, all right? So you see here, if you are using the 95% confidence intervals, you're going to get a lower bound that goes to 0.05. So it actually includes OLS. OLS does not include the two-stage least squares because it's a very precisely estimated 0.07, 7% increase in wages, but that's got very large, intervals. So what they do to improve the precision of two-stage least squares, they put in more instruments. Why? Because if you put in more instruments, you are going to have more variation in the predicted schooling. And if you have more variation in the predicted schooling, it will drive the standard errors down. Okay, so they're wanting to get more precise estimates so that they can conclusively rule out certain effects. Okay, that's what they want to know. So they decide to put in 180 instruments. How? What they decide to do is take their quarter of birth instrument and interact it with every state dummy and every year of birth. So what that means is, so Dong Lee, I don't know where you were born, but let's say you were born in California, okay? And I'm born in Mississippi. But we have the same quarter of birth. And maybe you were born in like 1995 and I was born in 1975. We're going to have different predicted schooling because we're going to have different coefficients on these interactions as well as the raw dummies. All right. So that means now I have different predicted schooling for every person. All right. So 50 state of birth dummies gives you more variability in education in predicted education. So now two-stage least squares. Well, Anna, that's kind of where we're going, actually. I mean, you can identify it. It can be identified, but it can introduce a weak instrument problem. And that's what we're talking about right now, is that the more instruments you have in there, if they are weak instruments, okay, then if they are weak instruments, so it's like if you know the correlation between the instrument and schooling with these in any of these interactions is not very strong, this is going to be the example of the weak instrument problem, and it's actually not easily testable. It's not as easily testable. The literature has not agreed on how to go about doing this, even though they've kind of agreed on the one instrument or the just identified instrumental variables. All right. So look what we have here. OLS is always being compared. Okay. It's not always the same. It's not always the same because they're putting in different controls. But watch. So here, excluded instruments are 30 quarter of birth time. So they always use the 180 instruments. They just start putting in more fixed effects or age squared. So look, once they put in all that stuff, the standard error went down. It had been 0.0161. Standard error goes down. All right. Then they start putting in age. Standard errors went up a little bit, but the coefficient went down. Then they put in region of residence dummies, not state of birth, but region. And then they have all of it. And still not got a lot of covariates, but you don't need a lot of covariates if you have IV. If you have a valid instrument, technically you may not need any. It just depends on if you think you need the covariates, because there might be some remaining backdoor path. Okay. So oh, I messed up the thing here. Okay, so so here, notice the two-stage least squares, 0.0811, 0.0891, brought the coefficient down, brought the standard errors down by about 40%. And so what they basically show is that, well, so this was the big punchline. They say, we found the causal effect, and it's not really any different from OLS. When you look at the bandwidth, when you look at the intervals, it's not really, it contains OLS. And they basically go, OLS is probably fine because it's not statistically different from IV. And that's why it's like, it was really encouraging because they were saying, yeah, this is probably causal. But then there are all these papers that come out. And Becker was one of them. Do I say it? Becker, Nelson and Starts, Booz, and then this one, Bound, Yeager, and Baker. He called it BJB. So here's what we're going to do. It's an important paper showing that OLS and two-stage least squares are pretty similar. Introduces this modern notion. I mean, that's not probably true. Well, yeah. That's probably true. Modern notion of trying to get your hands on plausibly exogenous instruments. Okay. But in the early 90s, there were all these papers that start to show up that it's not enough to have plausibly exogenous instruments, that you could have weak instruments, and it's particularly bad if you have many instruments. If you have exactly is the excludable instruments is what I'm talking about. If you have many instruments for the one endogenous variable, if any of them are weak, this weak problem starts to show up, and all these papers start really talking about it. And here's what you find. In the worst case scenario, and I'm going to show it when we come back, that if the instruments are so weak that there is no first stage, meaning that there is no correlation, really, statistically, between the instrument and the treatment variable, then the sampling distribution of two-stage least squares is centered on the probability limit of the bias of OLS. I don't know why it said OLS, but the OLS bias. Okay. So let's take a break. Let's come back in 15 minutes, 3 minutes on the hour, and we'll be right back. All right, let's get back to business. Okay. All right. All right, so let's look at this weak instrument problem. What exactly is going on here? So we have this causal model, right? I've changed the notation. I need to just sit down and like go back and, you know, make sure I have the right error term here. And I put an X in, just kind of more general. And I just got to sit down and do it. But let's just stay, okay, let's assume this model of interest, all right? Y equals beta X. And then we have these instruments. It's a matrix, all right? With the first stage equation, this, right? So there's the endogenous variable, and there is the first stage, okay? And then you have V. If V and if V and eta are correlated, then OLS is biased, all right? Then OLS will be biased. And to show the bias of OLS, just because this and that are correlated does not mean that and that are correlated, FYI. So to show the bias of OLS, what we're going to do is we're going to take the population mean difference in beta that we've estimated using beta OLS. We're going to imagine what we're doing is we don't know this, all right, but we're going to write out its properties. We're going to say on average, what's the size of the bias? Because if that's the average, if you take the average of a sampling distribution, meaning like imagine you had 10,000 random draws from the population, 10,000 different data sets, and you ran OLS, 10,000 times, okay, you'd get like a distribution of coefficients. I can like draw that just for those that would benefit from that. Okay. And then we do something like this. And then that right there would be like, expectation. This would be like beta hat. Be like expectation beta hat OLS, even though all of it is the beta hat from all of these like 10,000 draws from a population, which gives you 10,000 different data sets, and you run 10,000 different regressions and you get 10,000 different coefficients. That's the sampling distribution of the coefficient, okay? And it's a random variable because it's a function of the sample, which is random. It's a random draw from the superpopulation. So you've got this distribution, and here you've got the truth, all right? So maybe this is like the truth, all right? So that's like true. So then this right here is the bias. That's the bias of OLS. That's the OLS bias. Okay. So the question is, what's the bias of two-stage least squares with a weak instrument, and how does it relate to that horizontal line, right? So if the V and eta are correlated with each other, then essentially this drops down to the beta hat here. It's going to be the bias of it can be expressed as that right there, the correlation between X and V. And this is going to be covariance V and X, and that's basically a regression coefficient, but you can't, run it because you don't have that variable. But if it's like, if these two things are correlated, then that's not zero, right? Then this covariance is not zero. If they are not independent of each other, okay, then that covariance is non-zero. And so you have bias. And then you can rewrite it, since X is a function of eta, okay, then you can rewrite it as sigma Vn. Where does the Z go? Well, the Z is independent of that. So that part does go to zero. All right. So you have here an expression of the bias of OLS. That's the bias of it. Okay. Covariance of V and eta. My one cat is about to mess with the other cat. And the variance of eta. And that's, just kind of as a pause, it's kind of interesting. That is literally a regression coefficient. It's as though you ran this regressor, this outcome onto that variable only, okay? And if you could, that's an error term, so you don't know it, but error terms are random variables. So they are in principle a column of observations. You don't have them, okay? So they're supposed to be, if this right here is correlated with that, then it means these two things are correlated, right? So our hope is that with two-stage least squares, we can drive this bias to zero. Okay, we can drive this bias to zero in the finite sample, have a reasonably unbiased estimate of beta. Strong instruments shrink that with a shrinkage coefficient. It's going to shrink it to an inconsequential scaled value, but it can't go to zero. Cannot go to zero in the finite sample, because in the finite sample, because it's this ratio of the bias is this ratio, in the finite sample, it's like that won't be zero in the numerator. It'll be something, and that'll be a positive number, okay? But that won't be exactly zero. So, depending on, as you get a smaller and smaller sample, in principle, it's going to be even bigger. So a lot of this stuff that we're talking about with this weak instrument problem, the stuff that we're talking about is it's coming out of your data set being too small. All right. So strong instrument, it's not coming from exclusion. Exclusion's holding. It's coming from your data set being too small such that you can't drive that to zero. It drives to zero in the infinite population, but it does not drive to zero in a normal sample. In some simulations, the sample has to be massive in order for weak instruments to work, okay? So strong instruments shrink the bias term to an inconsequential scaled value, cannot go to zero. And I used to go through slide after slide after slide of exactly where this comes from, and it takes too long. It's in mostly harmless econometrics. I encourage you to read it and go through it. They start here, they go through a little bit of some algebra, and they get to this expression. Now, right here, what is this? That's the OLS bias. Okay? That is that, horizontal line. It's the bias term, right? It's that horizontal line that I drew. It's the bias term of OLS. And so this right here is that shrinkage operator, for lack of a better word. It's this, it's coefficient on that. It's a scalar coefficient because it's 1 divided by f plus 1, where the f is the excludable f statistic, the f statistic from the first stage on the excludability of the instrument from the first stage. If it's a 0, okay, imagine now what goes on. With a weak instrument, F equals, approximate 0. Okay, with a weak instrument, F equals approximately 0. And so the bias of two-stage least squares with F equals 0, weak instrument, very weak instrument, the bias of two-stage least squares is the bias of OLS. That means it's centered on the sampling distribution, the bias from the sampling distribution. Okay, the bias centered on the bias of OLS. Okay, but what if it is what if it's really big? Let's say it is 105. Okay. Well, if it's 105, that's 1 over 106. That's still not 0, but it is inconsequential. All right. It's inconsequential. Now, in the infinite sample, it will be 0 because in the infinite sample, that will be 0. All right. So it won't really matter over here. That'll be 0, but the scaling term comes out and they work through it. They work through the whole thing. All right. So you can test it. You can test this with an F test on the joint significance of Z in the first stage. And so it is absolutely critical that you choose instruments that are strongly correlated with the endogenous regressor. Otherwise, the cure is worse than the disease because the bias will be the same, but the variance will be larger. Remember? Because you get this larger variance with two-stage least squares. So you've not gained anything, and now you can't reject even more things. Okay? So, okay. So adding in more weak instruments, and this is kind of that comment I made earlier, what's lazy causal inference? Lazy causal inference, think back to what Orley said. Not only did they not check their first stage, they didn't even tell you what the instrument was. That is incredible. Some papers in the 90s, I won't name names, but some papers in the 90s, they'd write multiple papers on the same topic. And in one paper, the X's are covariates, and in the exact same other paper, on the same outcome, the X's are instruments. It was like it was very unprincipled. Prior to this causal inference revolution, well, that's what we're going to look at, Ligia. It used to be thought that an F of 10 was acceptable because of simulations by James Stock and Yogo, which Miguel had said. That was assuming homoscedasticity in those simulations. And under heteroscedasticity, that's not large enough. So we're going to see where the literature is now. So after Angrist and Kruger, there were these new papers. Well, before Angrist and Kruger, this guy is the guy that confronts Angrist. Angrist is literally just out of grad school. He said he went on the RES tour. That's kind of it's called the Restud tour. It's like it's like where all the new super duper stars of a certain year end up kind of all being chosen to go on the Restud tour. Peter Hull, who does these, who's going to be doing this design workshop later in April. He was on the Restud tour. He was a Josh Angrist student at MIT, and Angrist was too. And so he was on, after he did the Restud tour, he goes to Amsterdam, and Paul Becker goes up to him at a bar and just says, your paper sucks because it's got a weak instrument problem because you got too many instruments and it's, you got a problem. But Bound, Yeager, and Baker, it's a very technical paper. He's an econometrician. I don't actually know who Paul Baker is, but which doesn't mean anything, frankly. So Bound, Yeager, and Baker do a more of an empirical criticism. This paper, I think, ends up in Journal of Business and Statistics. And David Yeager is now at University of New Andrews, or St. Andrews? Yeah, University of St. Andrews. What is it? New Andrews or St. Whichever one's in Scotland. Baker, I don't know who that is. And this is John Bound. And Bound was Kruger's classmate at Harvard, St. Andrews, thank you. He was his classmate at Harvard. And he also was criticizing the paper because of the weak instrument problem, but he had a different approach. He was not going to actually see what Becker does is Becker just uses the paper. I actually think, no, Becker uses the job market paper by Josh Angrist, which is the Vietnam paper. He says the job market paper is screwed up. Bound, Yeager, and Baker say that the quarter of birth paper is screwed up. And they're going to not just talk about theoretical weak instruments. They're going to replicate the paper in a very clever way. What they're going to do is they are going to take the census data. They're going to reconstruct the sample. They don't get the exact same thing, but they're going to reconstruct the sample, run the OLS term, run IV on 108 instruments. Okay. It's just that it's not going to be the real instruments. What they're going to do instead is they're going to generate fake quarter of births. They're going to generate fake birthdays, not the real ones, fake ones. And then they're going to draw from it a quarter of birth from a fake date of birth, because in a random variable, a random draw from like some distribution, that cannot be correlated with schooling because that's just noise. And he's going to put 180 of them in. He's going to do it slow. Here he does. So here they do just the 3 instruments. And when they do that, they find a much larger IV. The F is actually weirdly enough big, 13, which is kind of something to be thinking about here. And but they don't have very many covariates. They don't have much in here. But anyway, the coefficient was not what they found. Their coefficient was like 0.08 something. That standard error is a lot bigger too. They had 0.016. That's nearly identical. Okay. Then what they do is they put in 30 excluded instruments. They're interacting quarter of birth with year of birth. Year of birth was 10 years, or it was 9 years. It was 9 years, and they had to omit one. So it was 9 times 3 is 27, plus the 30. So that gives the 3, you get 30. It draws it down. Look, that's almost identical. Then they do 180. That is basically identical. 0.083 with a standard error of 0.009. Let's see what theirs was. 0.083, 0.081, 0.0109. It's nearly identical, even with noise as the instruments. So there's this excellent review by Khaing and Neal, Practical Guide to Weak Instruments. And then there's also this weak instrument review by Isaiah Andrews, who won the John Bates Clark Award, I think 2 years ago, James Stock and Sophie Sun. So the two of them are very useful. And here's this paper. It was a collection of papers by James Stock and Yogo, but I'm going to look at the Stock Wright and Yogo 02 paper, which I thought was the site, although maybe it is Stock and Yogo and Miguel is right, or maybe there's two. But anyway, I have here Stock Wright and Yogo. So they found in their simulation that the F statistics on the excludability of the instruments from the first stage, if they were greater than 10, they performed well in Monte Carlos if you had homoscedastic errors. But two-stage least squares has poor properties here. It's underpowered. You end up still with artificially low standard errors when endogeneity is severe, and your t-tests are misleading. Here's what Andrews, Stock, and Sun say. In the leading case with a single endogenous regressor, which means in the leading case with one treatment variable that is endogenous, we recommend that researchers judge instrument strength using a different F statistic, the F statistic of the Montiel, Olea, and Pfluger 2013, which is identical to this other one in a just identified case. If there is a single instrument, okay, there is a single instrument. We also recommend reporting this old paper by Anderson and Rubin, not Don Rubin, Anderson and Rubin from the 40s. It's called the Anderson and Rubin confidence intervals. If you have a single instrument, don't just report the F from this other F test, also report the Anderson-Rubin confidence intervals. Anderson and Rubin confidence intervals are robust to weak instruments. So even if you have a weak instrument, you can get confidence intervals that have correct coverage. Okay, they're effective regardless of the strength of the instruments. They just might be really big, which is what you need to know. So they should also be reported regardless of the value of the first stage F. Okay, and if there are multiple instruments, then the literature has not yet decided on the single procedure. But we recommend choosing from among the several available robust procedures that are efficient when the instruments are strong. So Anderson-Rubin greatly alleviates this problem. It's not an F. I'll show you what we did in our paper that did it. Says it's unlocked. Let me show you how we did it. The appendix. Okay, here's what we did. Here. These are all outcomes. They look like covariates, but we had 6 different outcomes. We have over here the information about it. We have the Anderson-Rubin test in brackets. So here's our coefficient estimate from two-stage least squares. There's our standard error. Here's our Anderson-Rubin confidence intervals. What we did was, that's the Pfluger. That's not the Olea and Pfluger. Oh, that's the state of command. So we do this. Now, technically, you're not supposed. I heard somebody say if you report the Anderson-Rubin confidence interval, you're not even supposed to look at the point estimate. You're just supposed to say it's in there. Yes. Yeah. That's right. So this is confidence intervals you would put under probably the standard error, and it's the Anderson-Rubin. This is here. Kleibergen and PAP F. Okay, 428. Right? Read down here. Each column gives the corresponding clinician and inmate robust two-way clustered standard errors in parentheses. Robust first stage F is reported. It's called the Kleibergen PAP. It is equivalent to Montiel-Olega and Pfluger in this case of a single instrument. So that's what we did. We report the first stage regressions with an F. All right. And then we report over much later our IV model. We had two-stage least squares and IV lasso. All right. Because we had one just identified, and then we did it a different way with multiple instruments. And when you're doing multiple instruments, you got to be careful. So, there is evidence. Paper came out in American Economic Review that found that the first stage F needs to be much larger than 10. They say it needs to be 105. Higher thresholds for the F are recommended. Even then, robust tests are suggested unless F is in the thousands. So Keen and Neal write, to avoid over-rejecting the null when two-stage least squared is shifted in the direction of the OLS bias. That's what we just talked about. One should rely on Anderson-Rubin test rather than the t-test, even when the first stage F is in the thousands. Okay? All right. So, something that keeps coming up was this issue of heterogeneous treatment effects. So, the paper that Angrist and Embens win the Nobel Prize for, well, it's not really a single paper. It's more of the work they did on heterogeneous treatment effects and instrumental variables that they showed what the interpretation of the coefficient was when you had heterogeneous treatment effects. Okay. Historically, instrumental variables was always modeled using realized outcomes. We saw that when we did Wald. All right, let me just not go back. When we did Wald, when we did the Wald estimator, okay, what we found when we did it, when we derived what the Wald estimator identified, which was a causal effect, what did we do? We only looked at y. We said covariance yz divided by covariance zd or zs, right? It was always the realized outcome, okay? But everything we've done before today was about potential outcomes, okay? So in 2021, they win the Nobel Prize for their 1990s work on IV. Sure. Yeah, I can do that. I can do that, Akash. So Josh Angrist goes to Princeton and he gets the idea for his job market paper from Orley, actually. Orley Ashenfelter is what I've heard anyway. Something Orley said, you know, somebody needs to do a study like this, and Josh goes and does it. I mean, I think Orley Ashenfelter was just like a font of endless creativity, technical skills, endless creativity. He's not an econometrician. That's it. That's it, Artie. I must not have updated it because it got published. So it's been published. Yeah, I forgot about that. I need to kind of go clean some of this stuff up. So he writes that dissertation, and the thing that makes this so interesting is he's not using just like whatever for instruments. He's using physically randomized instruments. Okay, he's using physically randomized instruments. What he basically is doing is he's going to Vietnam. Or he's not going to Vietnam. He's going back to the Social Security Administrative data set, and he's able to know who goes into the military, and he knows their career earnings because he's got this like Social Security data, and he knows their draft lottery number because the draft lottery numbers were based on their birthday, and so he could use an algorithm that gave everybody, it was called something, it's called the numbers, it was some kind of word, but it's like a random number. And so he knew everybody's instrument. And so it was literally like actual like coin flips, okay? As opposed to like, I'm using as my instrument this kind of event or this kind of thing, which is not literally like random. It's usually what was called excludable, okay? But he writes a dissertation he goes to Harvard. He gets there in 89 or 90, one of them. And Hito Embens, also ends up going to Harvard, but it's kind of random. Josh Angrist is literally a superstar. He's a superstar. He goes on the Restud tour. He's one of the strongest candidates that year. Everybody's fighting for him. And he takes the job at the premier American institution, Harvard, maybe MIT too, but like he goes to Harvard. All right. He's there for a year. Hito Embens he's at Brown University. Okay. Which is a good school, but I don't think it's at the level at the time of like Harvard, MIT, Princeton. And he does not even get an interview at the annual conference in economics. We have this annual conference called the ASSA and American Social Science Association. He does not get an interview. This guy named Gary Chamberlain, a very famous econometrician who died a couple of years ago, Gary Chamberlain calls him on the phone. And Gary Chamberlain says, we're going to need somebody to teach probability and statistics. And would you like to come? And it's not like it's a tenure track job. Would you like to come? And Embens is like, yes. And what's interesting is Embens said he had always felt, coming from Brown, he had always felt that he was overplaced. I don't know if that term is used outside the United States, but overplaced means it's like, you know, kind of when your girlfriend is way too attractive for a person like you know, you think, or whatever. It's like, you know, it's kind of like, I'm definitely out of my league. He sort of felt like that, he said. And immediately, though, he lives in faculty housing, and so does Josh Angrist. And they, by legend, you know, they would always do their laundry in the faculty laundry room together, and they would talk about their work. And there is something that happens. I can't help it. I want to tell this story. So I'm not going to do both of them. That's what I'm not going to do both of them. I'm just going to do one of them. We won't do the full 10 minutes.
I was wondering, it's not really clear. It's hard to hear these stories in the past because you can't really imagine what was going on at the time. You just kind of have these like all this kind of survivor bias where all I know is your work, and that's the work I remember. And so I was just kind of wondering, what was the context at the time of like that broader community and the debates that everybody was having, and what did they think about the work that you and Embens were doing?
Well, that's two distinct questions. So let me talk a little bit about the context, because there were some key contributions there. Gary?
So here's what he's going to say. He's going to set up this paper, all right? And he's going to say, our paper does not just like this, it's this econometrica paper by Embens and Angrist, 94, I think, or 95. And he basically says, this is the paper that came out of the 1 year that Angrist and Embens overlap, because Angrist leaves to go to Israel after being there for only a year. Embens stays the whole time. Embens, interestingly enough, ends up getting denied tenure at Harvard. I don't know of another case in economics where a Nobel laureate was denied tenure. So it just goes to show you it. And there's a theory I have that his getting denied tenure is a huge part of the story of the causal inference movement, but I'm not going to do that right now. So this paper does not come out of nowhere. There's earlier work. All right, so here he goes.
That had a couple papers that were actually sort of negative results. So he had a results showing that you're never going to get the average treatment effect effectively. I mean, his papers are very technical, but this is an implication. If the probability of selection isn't driven into the tails. In other words, it has to be driven to 0 and 1. And I think for the purposes of this kind of discussion, there's not really a big distinction between the effect of treatment on the treated and the effect of the average treatment effect. You know, so, and that was why the Bloom theorem worked, because actually you had a group where the probability of treatment was 0, which is what happens in a latent index model when the covariates have infinite support. Then with some, you know, vanishingly small probability, but never, the probability of treatment is driven by a covariate that has infinite support into the tails. And Heckman had a result in a 1990 paper that I think was actually in the Papers and Proceedings, a very brief paper, which had a version of that idea applied to treatment effects. Gary's result was more general, about sort of sample selection problems of all kinds. And Heckman's result was later kind of christened as identification at infinity, or maybe Chamberlain came up with that. But it was sort of seen as a negative result because, you know, it's not going to.
Negative results are basically like theoretical results where it's like, okay, we solved it. Here's the situation where you can do this tool. And then they lay out what the situation is. And it's like, okay, this will never work. The situation where you could use it will never be reality. And what James Heckman is doing is he's saying, here's the situation where instrumental variables will identify the average treatment effect. which remember, average treatment effects are like one of the parameters that we really cared about on day one. And and yet that's like a potential outcomes interpretation. Okay.
Happened, it's sort of a version of a technical thing that kind of never happens, but it's true that a normally distributed random variable can be plus or minus infinity.
Right.
So what does that really mean for empirical work? You shouldn't count on it. And also thinking on these problems was heavily influenced by kind of the latent index workhorse.
Mm-hmm.
And that I think proved.
And so that's the other thing, this thing called the latent index this latent index model. In the history of econometrics, this latent index, if you go back, if some of you have seen it, a lot of you have probably seen it. It's used in like your qualitative dependent variable classes where you're like looking at logits and conditional logits and all this stuff. And where it's like, if X goes above X star, then something will happen. It's like this latent variable. So this latent index is an approach that econometricians have technically taken that doesn't use potential outcomes. Okay, so he's talking about latent index models.
Quite limiting because the latent index model is basically telling you that you need a covariate that has infinite support. Because the latent index model with continuously distributed errors isn't going to produce that Bloom scenario.
Right.
And you could replicate this on your computer. If you try to run the first stage for the Bloom problem with probit, you'll get an error. It won't do it. Because probit probabilities can never be 0 or 1, probit or logit.
Right.
And sometimes I have my students do this.
Yeah.
So you need to get out of that somehow. So that's one thing that Hito and I were willing to do. We weren't wedded to the latent index paradigm, even though we wanted to understand it.
Right.
So there were these negative results, and Heckman had the paper with Rob, which was a very comprehensive review of what was known about treatment effects at the time. I'm sure you've seen that.
Yeah.
I was studying that, like the Bible.
Mm.
And, I had focused on the section there on IV, which really was not, it was mostly discouraging. It's kind of like you need constant effects to.
So here we have like this, it's this Heckman and Robb 1985 paper. I think that's what he's talking about. And it's this like famous paper. It's where the term selection on observables is coined, I think. Anyway, and he's saying it's very negative about IV, but it's not negative about IV like for exclusion or like practical stuff. It's negative about IV for these issues that he's talking about, because the paper is like about treatment effects, heterogeneous in nature. And he's basically saying you're not going to be able to recover any parameter that's interesting, unless you have this weird scenario that's all this very technical thing about the pushing the probability of treatment into the tails of an infinite thing or whatever it was he was saying. That's like the situation. So he's reading it and he's go, Heckman is basically saying you can't do IV. He didn't come out and say it that you can't do IV, because you could. There's like this one little knife edge condition where you could do it. But when you really understood it, which is what Angus is saying, it's not going to work.
Right.
So we saw that as a big methodological challenge.
Yeah.
And we had applications that sort of left us feeling like, well, it can't be that IV is worthless. If you think about, the draft lottery, it can't be that you only get something out of it when the effects are constant.
See, and this is where he's going with it. This is what's fascinating about this origin. It's actually, you've got here the econometricians, all right? Chamberlain, Mansky, who's not talking about, and Heckman. It was so pessimistic, this like negative result stuff. It was so pessimistic because they all just kind of painted out a theoretical situation. It's all purely theoretical, where the situations where IV would identify an average treatment effect, let alone the average treat on the treated, but like the average treatment effect is basically never going to happen in the real world. All right. And yet, this is what's fascinating. It's Josh's job market paper. Even to Hito, who's an econometrician, it's Josh's job market paper that really seems to get both of those guys stuck. Because they keep thinking to themselves, I have a coin flip in the first stage, and there is no way that this coin flip could be driving the outcome. It's satisfying exclusion. It's satisfying the first stage requirements. How could it be possible that you're learning nothing? See, that's subtle. That's very subtle. Heckman, Mansky, Chamberlain are saying you cannot learn anything about the average treatment effect. But Josh and Embens are saying something different. They're saying just because you can't learn something about the average treatment effect does not therefore mean you cannot learn anything. See how that's a little bit different? Because there's lots of different parameters.
Some intuitive sense in which there are men who are conscripted that wouldn't have served if they hadn't been conscripted. We must be learning something about these guys.
Yeah.
So that was the context, Scott. What was the other question? Oh, what was the reaction to what we were doing?
Yeah.
The reaction was mixed. You know, I would say Gary Chamberlain, you know, to our great good fortune, was very excited about what we were doing and gave us extremely important feedback along the way. And actually, Hito and I had a version of the late theorem that kind of relied on a latent index setup.
Yeah.
And Gary said, you know, you don't really need that. You can just define potential assignments. And that was a wonderful insight, which simplified the presentation of the theorem, and I think also made it much more appealing outside of economics to people like Rubin.
Right.
That we didn't have the superstructure of latent index, which was really a very economic model that didn't seem widely applicable.
So this is kind of interesting. All right.
People were critical of it, I think.
This is really kind of interesting. He said two things. I actually do want us to listen to Embens' part of the story because we haven't listened to him since the first day. But it's really kind of interesting what he says. He says Gary Chamberlain makes a suggestion. All right. This is and in Angus. Okay, yeah, I saw your thing wrong. So Gary Chamberlain makes a suggestion. Not everyone. Doesn't have to be everyone. Gary Chamberlain makes a suggestion that actually, Ronald, that was what the thing was. Heckman and those other guys say that the instrument to identify the average treatment effect literally has to move everyone into and out. Everyone. And you can see in Josh's dissertation that that is not what the draft lottery did. So that was kind of part of the issue. But what Angus just said that was really interesting. Angus says that Heckman and Robb, 1985. Heckman and Robb, it's a very famous paper. It might even be in the thing. I'll look in a second. He says when they switch from using the latent index model, when they switch from using the latent index model, it changed things. Two things that changed. First of all, the late theorem was like the proof was like a couple of lines. Whereas when they were using the latent index theorem, the latent index models, it was just pages and pages of proofs. It was all these integrals. It was really hard for people to understand. Okay. Second, it was also, though, that the latent index thing was stuff that econometricians used. It was not stuff that statisticians used. Statisticians were using potential outcomes. Donald Rubin had been using potential outcomes since the 70s. Donald Rubin is in the stats department at Harvard. Hito and Josh go over to the stats department to Rubin, showing them the work, and they collaborate and come up with a 96 paper in the Journal of American Statistical Association. Those are the twin papers that are considered to be the foundations for this stuff. But the point here is that when Gary Chamberlain makes this suggestion and they don't end up using that latent index model and they use potential outcomes, Angrist and Embens both say instrumental variables got freed up from economics because it had been an economic tool. Remember, economists had invented it back in the 20s. And it was not widely used. But once it got its foundations in statistics and not econometrics, then at least these guys believe that that is what brought a broader attention to the work of this causal inference within observational work. Now you don't know that for sure, but that's kind of like their interpretation of their own influence. So let's look at this. And I literally love watching this. You can kind of tell.
As well. You know, it's a paper that's gotten a lot of attention, but still not nearly as much, I think, as its importance would justify.
Yeah. You know, it's because I'm 46 and graduated in 07, I've only lived in your timeline. You know, I've only lived in the wake of your work. So I don't really know what it was like at the beginning. And so am I right that this was the work that you were doing with Angrist and Rubin wasn't always received well within the economy?
See, I heard that. And I think most people know it, but like, I didn't really know it. I was always kind of surprised. A lot of people did not like this paper. Heckman did not like this paper. I think Heckman had a fairly low view in general of the work that Angrist and him were doing. And maybe even in general, doesn't matter. But a lot of the econometrics community was not super enthusiastic about this work that they were doing on IV. And that's kind of, honestly, at this level, you know, there's a lot of fighting. There's a lot of fighting that takes place. Embens is the sweetest man in the whole profession. He's just a sweetheart. And he's brilliant. And he's got a very open mind. At least he did, you know, in the beginning. He said he's got less of an open mind now. But I'll just tell a real quick anecdote about how I knew this. I think it was like, because I went to the University of Georgia. It was and the University of Georgia was playing in in the National American Football Championship. It's called the NCAA tournament in college against the powerhouse team in America, University of Alabama. And I just wrote Embens. I didn't even know him. And I was like, but I was going to go to this continuing education class that he was doing. And I said at the annual conference, and I was going to be there a little bit longer. I was like, hey, a couple of us are going to go to a bar and watch the Georgia Alabama game. Do you want to come? And he was like, sure. He hadn't won the Nobel Prize yet, but he was like, sure. And he comes. And I like made note of that. He didn't know any of us. Okay. But he just like goes. And that is what I started to realize about Embens, is that he, for some reason, has this like weird open-mindedness, because the econometricians were kind of closed-minded about IV because of this series of papers. And Embens was affected by Josh's job market paper to basically sort of be like undeterred, not like violent or anything. He just was kind of open-minded. And when he gets denied tenure, he talks about it here. When he gets denied tenure, he says, you know, I always felt like I was overplaced. I was kind of excited about going out to UCLA because the temperature, the weather was different. You know, he just kind of was always open to new experiences. So it's kind of, he's really a fascinating guy. So here we go.
Community, or is it, that's not really the way things were?
Yeah, and I mean, that's right. There was, I think early on, there were a number of people who thought this was really interesting and really innovative. So Gary Chamberlain was kind of a big fan of the work early on, but also people like Whitney Newey thought it was very interesting early on. And so I remember the first time I presented it at Harvard, and people were very curious about it. But at the same time, and so possibly kind of partly the reason for why people were curious, because there was also a lot of people who thought, no, this was the wrong way to go. This was kind of just not the way things were being done. And they, you know, I think one of the specific criticism was that, you know, you should start by saying what you're interested in. You should be clear about what you're interested in, and then focus on estimating that.
Right.
And what we did was kind of turn it around a little bit. We said, well, you know, maybe you're interested in the average effect, but you can't get that, and so we'll just take what you can get.
Right. That was dissatisfying to some people.
Well, that was, you know, sort of cheating a little bit, saying, well, they felt that was exposed, kind of justifying doing what you were doing rather than being principled about trying to estimate something and figuring out how to best get at that.
So
And-
why did you and Josh and Ruben end up kind of going down that route if that was so not the way things were done?
Well, so from my perspective, the motivation came out of kind of this tension between Josh's thesis, kind of with the draft lottery, kind of where you had this instrument that seemed very credible, but it was only moving the fraction of veterans kind of from about 15 to 30% or something. And so there had been these papers by Heckman and Mansky in the Papers and Proceedings in 1990, where they kind of both argued that you couldn't actually identify the average effect of veteran status in cases like that. They weren't looking at that example, but said if you want to get the average effect of some treatment using an instrument, unless the instrument moves the probability of getting the treatment from 0 to 1, you can't get the average effect.
Right.
And so kind of on the one hand, there were these negative results saying, no, you cannot get the average effect. And on the other hand, there was this application that seemed very credible. That seemed like pretty much the best you could do, but it was very far from moving the treatment probability from 0 to 1. So we try to understand that tension and see if there was something credible you could learn from that. If it was not, and we didn't quite formulate it initially that way, but if you couldn't get the overall average, was there something else you could get? And so Mansky said, well, you could get the bounds, but that didn't seem quite enough for policy in a lot of cases. And so we wanted to resolve that. And initially, from my perspective, we were very neutral about it. We didn't say the local average treatment effect is the thing you're interested in. It was just, that's what you're getting.
Yeah, right.
Understanding that seemed useful to us. And,
so was the potential outcomes model, if you had to rank its importance in making those discoveries about the late theorem, I mean, were you going to get to it anyway, or is potential outcomes just really opening it up?
No, I think that really opened it up. Exposed the math is very, very simple. So initially there's two things there. But so initially we set up the selection problem itself in terms of a latent index model,
right?
Where there's some latent D star that follows some model, and if that crosses the threshold, you serve in the military, and otherwise you don't.
Right.
And so we got the late result in that way. It looks very messy that way, because we said, well, we have a continuous unobserved thing, and so we could have these integrals and stuff, and that. But the basic result was there. But then Gary Chamberlain said, well, actually, you could also think of the treatment status in terms of potential outcomes. And that then kind of the proof simplifies to being 2 or 3 lines. And it just becomes much crisper. And in fact, that also, so Don Ruben made a similar comment where he kind of looked at the argument and said, well, this kind of looks interesting, but it looks, if this is true, then really there should be a 2-line proof. There shouldn't be kind of a page of kind of integrals and stuff.
Right.
And they were both right. And I think that really simplified the exposition and made it much more, much clearer and much better.
Yeah.
So I think the potential outcome setup there was hugely important. And I actually remember at that time reading Rubens, I think it's a 77 paper in the Journal of Educational Psychology.
Yeah.
Where essentially all he does is talk about, you want to think of causal effects as the difference between Y of C and Y of T.
Yeah.
It's this contrast. And I remember reading that paper thinking, wow, that's actually a very helpful way of formulating the problem.
Mm-hmm. Mm-hmm.
And that is just much clearer than starting with these modeling things purely in terms of the observed outcomes.
Right.
And later, sort of around that, well, a little later, but sort of influenced by that, I wrote this book review of Henry's book on kind of with econometrics readings, where I look back.
That's it. Okay. I absolutely adore him. Every time I watch that, I just think how much I enjoy listening to him. So we're going to take an hour lunch. We'll come back. We'll knock out this heterogeneous treatment effects. We're basically almost done. And then we'll spend the rest of the afternoon on regression, discontinuity design. But I wanted to kind of go through that because, the rest of the IV stuff is not very difficult. It's not like there's new mathematics. We're just really wanting to understand, what are they talking about in this? What is it that instrumental variables is actually identifying? If it's not identifying that quote unquote average treatment effect, then like, what is it getting? And he alludes to it. They both allude to it. They say it's doing something called the local average treatment effect. But this is like the introduction of a new parameter. And in the treatment effects literature, it's the first time it's been articulated. So we're gonna take an hour lunch break, and we're gonna come back, and then we'll pick it back up. All right. So see you guys in a minute. Let's up and get into D. So here. All right. So one of the things that Angrist and Embens both said was they mentioned this guy, Gary Chamberlain, and they said Chamberlain recommends modifying Rubin's potential outcomes framework. Okay. And then they said, and I think it was Angrist that said to model, Embens said model treatment status using potential outcomes. So that's this. So this was an idea by Chamberlain, and Rubin said the same thing. And it basically allowed them to move away from using that latent index stuff to using stats. And when, using this potential outcomes framework. And when they did that, at least these guys think, when they did that, they were able to, quote, recover the statistics part of the room, meaning instrumental variables had been developed to really study economic concepts. And a lot of the underlying structure of it was solely motivated in terms of economics. And so if it's just solely a tool used in economics, then it's not very broadly applicable. But once it started to sit on top of this more universal language, there was two things that it did. It clarified what it was estimating and made it more generally interesting. Okay. So what they think is that part of what fueled this causal inference revolution was this very thing, which was to model treatment status using potential treatment, which is kind of like potential outcomes. Here's what it is. I am drafted into the military. So we're gonna let Z equal 1 drafted. Z equals 0, not drafted. They're both the instrumental variable. And it'll be binary. All right. Then we've got potential treatment status, D1. D1 does not have to mean that the person goes into the military just because he was drafted. He could always avoid the military service through a variety of mechanisms. He could be conscientious objector, he could flee, he could have a medical release, there could be all kinds of stuff. So just because he's drafted does not mean that he will serve. He could or he couldn't. And it's treatment, it's a potential treatment status because it's the same person, right? It just because he's not drafted does not, just because he's drafted, all right, does not mean, sorry, just because he is not drafted does not mean that he will not serve. All right. He could not be drafted and volunteer. Okay. So we've got this kind of situation here where just because what this is what is he going to do with regards to the military in two worlds, one where he's drafted, one where he's not. Okay. That's where we're going to start out. Okay. So then we're going to represent outcomes as a function of both treatment status and instrument status. All right. So we're going to do both. So you're going to have here, you know, a representation of the underlying potential outcomes, which is going to be, well, what's their earnings outcome, you know, in a world where they're not in the military, but they were drafted. Okay. Versus what is their earnings outcome in a world where they're not in the military, not drafted? And what's their earnings outcome in a world where they are in the military, but not drafted? And what's their earnings outcome in a world where they're not, where they are in the military and they are drafted? All right. So we're doing the same thing. It's just that instead of there being two potential outcomes, there's four. All right. All right. So here are the identifying assumptions. Here are the identifying assumptions that are needed for identifying a causal parameter using instrumental variables. We don't know what it's necessarily identifying, but in order for instrumental variables to have a causal interpretation, we have to assume five things: SUTVA, random assignment, exclusion restriction, non-zero first stage, monotonicity. So here we're going to be breaking apart this exclusion from random assignment. This is going to guarantee that it's not connected to the confounders, and this is going to guarantee that it cannot directly cause the outcome. All right. So here's SUTVA. In the IV context, SUTVA means that the potential treatments for any unit do not depend on the instrument assignment to other people, and there are no different forms of versions of each instrument level, which would lead to different potential treatments. So it's a version of the SUTVA that we looked at with regards to potential outcomes. So what we're basically saying is, you know, when Artie gets drafted, right? This is instrument assigned to other units. Artie getting drafted does not affect my decision to serve. Okay. That's what it means. So there's like independence. There's no interference between units, instruments, and another person's treatment. And then secondly, there's no different forms of the instrument level. So everybody's getting the same instrument, whatever it means. There's like an instrument dosage, and it's the same for each person, right? Number two, independence. The instrument is independent of the potential outcomes and the potential treatment status, which is to say it's random, right? It's ensured by physical randomization, but it could also be, you know, ensured by other kinds of assignments like that alphabetizing. The alphabetizing probably is going to be independent of a person's desire to serve in the military, because this D1 minus D0 is sort of measuring causal effect of the instrument on serving. And then this is measuring the potential outcomes. So a random draft number generated by a random number generator will satisfy this. Okay. Now here's what you get with those two things. let me just put here what you're getting. So we're gonna put the Z, D here, the Y, the U, right? So when we get both of those, okay. All right, so here's two situations. Okay, this will satisfy exclusion, and this does not satisfy exclusion. But both are random. Okay, meaning they are generated independent of those potential treatment statuses and potential outcomes. All right. So they're going to satisfy that, but they're not going to be they're not going to satisfy exclusion. All right. So keep that in mind. So what we're going to do is we're going to measure the first stage, and then we're going to measure the reduced form. Because remember, IV is reduced form over first stage. Sorry, that's what I was saying, Sebastian. If you go back, that's what I was trying to, I may not have said it right. SUDVA means the potential treatments for any unit do not vary. Potential treatments, which is what you're saying. Okay. This is the decision to volunteer isn't changed by somebody else's instrument. Okay. So it's not independence of the instruments. It's independent of one person's instrument and another person's willingness to serve. So there can't be any spillovers between the instrument and the treatment of other people. So you can imagine stories like there's movies where, you know, my best friend is drafted. I wasn't drafted, but I decide, you know, Hunger Games would violate it. When what's her face's sister gets drafted to be in the Hunger Games, she volunteers as tribute. So that would be like, you know, an example. Katniss, right? That'd be like an example of a violation of SUDVA because she wasn't even drafted, but she changed her treatment assignment based on the assignment. I do too. Yeah. So first stage measures the causal effect. So look, here we have, so this is one of the things independence gives you. Independence means that correlation between the treatment and the instrument is measuring a causal effect. No, SUDVA is not IID. SUDVA, yeah, I was thinking Saving Private Ryan. SUDVA is not IID. It's simply requiring there be no spillover in one well, IID has to do with the errors. There might be a way, Artie, to frame it that way. I'm not positive, but IID has to do with the random shocks. Not positive that that's the same thing as saying that. I'm not positive. So, yeah, I didn't think it was. It's not. I don't think it. I think you could probably have. I'd have to think about it, but well, actually, yeah, exactly. Because you could have this. You could have this right here. Error. Let it be IID, and you know, it's IID, identical and independently distributed, but this person's treatment assignment might be impacting somebody else's. So, okay. So we're going to write down the first stage as kind of like this, you know, difference in means. Average D for some average military service if you were drafted minus average military service if you were not drafted. We're going to replace D with D1 because in a world where you're drafted, I observe your treatment assignment had you been drafted. And if you weren't drafted, I observe your treatment assignment had you not been drafted. Well, here is what. Oh, great. Thanks, Lynn. So here's what independence implies. If Z is independent of D1 and D0, then you can write down this equality. Expectation D1 is equal 1 equal expectation D1 is equal 0. You can also write down this. Okay? Write that down. So if I know this right here, all right, expectation D1 conditional on Z equal 1, then notice the average of D1 it doesn't have anything to do with Z, so I can drop it. Okay, so I can just get rid of it. Because it doesn't depend on it. See that? Doesn't depend on it. It's always the same, so we can drop it. And D equals 0 doesn't depend on Z, so I can drop it. And then because of that, notice independence just says that when this is independent, then you can write this down. What is that? That is the causal effect of the instrument on treatment, which is to say, if the draft lottery is random, then comparing groups of people drafted to not drafted yields the average causal effect of the instrument on military service. Okay? It's an average causal effect. And now we have the implications of independence for the reduced form. So we're going to write this down here. Okay? So I've got these two things up here. This one satisfies exclusion, this one doesn't. Independence, if that is independent, you will be able to say when you compare earnings for those drafted and earnings for those not drafted, both of these situations, whether exclusion holds or doesn't hold, as long as you have independence, you can always say that the effect of the instrument on the outcome is causal. It's just that here it only operates through military service, and here it operates through both. Okay? Here it operates through both. And you can see how it happens. So here, expectation Y is equal 1, expectation Y is equal 0. Replace it with their potential outcomes notation. We say 1, if you were treated, is equal 1, minus 0, not in a world we're not treated. You don't know if that they're not in the military though, but you know they're not treated. They're not instrumented. Z, conditional on being not instrumented. Well, Y is independent of Z, so we can just get rid of that. We can just write it as expectation Y is a function of D1, expectation Y is a function of D0, and this is going to give you the average treatment effect. Sorry, not the average treatment effect, the average instrument effect. Okay, if you just compare earnings for those military versus not, sorry, if you compare earnings for those drafted versus those not drafted, you will get the causal effect of drafting on earnings. You just won't be able to say how much of it's due to military and how much of it's not due to military. Okay. All right. So then we put in exclusion. And what exclusion says is if you keep treatment status the same, right, but you vary the instrument, if the earnings don't change when you vary the instrument but keep that the same, then you know exclusion holds. Okay? So that means exclusion means, see here, I could keep that the same. All right, so I could keep that the same. I could go keep that fixed. Keep them both fixed. But if you vary the instrument here, you'll vary the outcome, even though you're not changing military. So that is why exclusion doesn't hold. But if you keep military enrollment fixed and you start changing whether or not the person was drafted, earnings doesn't change. So that's what exclusion means. So that's what people mean when they say the instrument affects the outcome only through the treatment. Any effect of Z on Y must be via the effect of Z on D. Whereas here, we said, well, it's an average effect. You just don't know if it's coming through the military. Here, exclusion means it's only coming through the military. So a violation would be your draft number causes you to go to graduate school to avoid the draft. Well, graduate school will change your wages, independent of whether you were drafted, independent of whether you go into the military. So exclusion could be violated, even though instruments were random. All right, so we go through here. I'm going to skip this part. So what you've got to know is you've got to know your treatment and your instrument assignment mechanism. People tend to target exclusion arguments when they see them because, except under very special situations like homogeneous treatment effect with over-identification, they're based on untestable assumptions. And this is what Angers and Kruger said in 2001 in a journal article. They said, in our view, good instruments often come from detailed knowledge of the economic mechanism and the institutions that determine the regressor of interest. So you simply cannot avoid the importance of knowledge of institutional details. That's why when I in this paper, so I know that Angerson Kruger paper 2001. So I've always felt like the only way you could ever do IV is you got to know the assignment mechanism. If you don't know the assignment mechanism, it's going to be really questionable. And that's why I would take this one lawyer out to dinner all the time, because I really wanted her to explain how is it that people got into this mental health court. And what she finally explained was that you're getting a randomized clinician, and the clinician is assigning a mental health score. And that's when I started to realize, oh, I've got independence, because the assignment of the clinician has nothing to do with their suicidality, and it has nothing to do with their potential, mental illness. It's got nothing to do with either one of those. Okay. Question for me was, could it have violate exclusion? So if you go back to this, here. Okay. So what I had to really figure out was there any way that the randomized clinician could be impacting whether or not the person tried to hurt themselves, whether or not can clinicians directly affect suicidality, or is it only through the mental health score? And there was so that's what I had to do. Then we have to have the strong first stage, that the causal effect must be statistically different from, must be large. Not the treatment effect must be large, but the correlation must be large, highly significant. And then there was this new assumption that never showed up in the old instrumental variables literature. It's not, and what it is called is monotonicity. So if you only know the two-stage least squares assumptions under constant treatment effects, there is no monotonicity assumption. So I'll have to read that more closely, Nita. So monotonicity, what does it mean? Pi is the reduced form causal effect of the instrument on treatment status. All right, here we go. So this is the causal effect of the instrument on treatment status. What monotonicity requires. So for the economists in the room, the non-economists won't know what I'm talking about, but the economists in the room, if you remember from your micro class, your micro 1 class, you would see, okay, so everybody listening, we would, in our micro theory classes, in our microeconomics theory, everything's about consumer behavior, or not everything, consumer, producer, markets. But one of the things in consumer is you introduce this idea of utility. And utility is a function. And all that it means is it kind of captures a person's ranking of the world. All right. And we would kind of go through, we would say like, well, if the preferences are like blah, 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 blah. And then there was a like additional assumption that you would learn, which is when you go from the preferences into something called the utility function, there would be this additional thing that you would often introduce. It wasn't always required, but for some of the results in economics, you would have to assume a math equation. And the math equation was different than the preferences. The math equation was assume that exactly, Eduardo, indifferent. So assume that the utility function is quasi-concave. This is something you would learn all the time in your first exposure at theory. And what was it? It was a shape restriction. It was a restriction on what Eduardo just said, which is the indifference curves. Yeah. So it allowed for that quasi-concavity had all these like little properties that was kind of like, and I won't get into it, but it was a mathematic restriction on the utility function. It didn't allow for a variety of preferences. It sort of just was focused on this like one particular thing that was curved. All right. That's actually what monotonicity is. Monotonicity is a shape restriction. It's different than the 4 things we just talked about, which had more of like a behavioral kind of more interpretation, you know, or it was like more statistics. Monotonicity was a thing that Embens saw that he was going to need this in order to get parameters. Sorry, without monotonicity, the IV estimates will not give you a weighted average, a positively weighted average of these underlying treatment effects. Without monotonicity, you can have negative weights, and these negative weights will start canceling out the positive weights, and you can't interpret it in a causal way. So what is monotonicity? Monotonicity means kind of like what the title means. It means that the instrument is either always non-negative or always non-positive, but it can't be both. Right? So it can't be that people with high draft numbers dodge the draft. All right. So that would be here. I have a large draft number, and when I have a large draft number, I dodge. Okay. Cannot be simultaneously that had they had a high draft number, they would have dodged, and had they had a low draft number, they would have volunteered. It cannot be that they are always like breaking the rules of whatever their instrument assignment is. That's what it means to be monotonic. Okay. If you have all 5 of them, then what happens is that instrumental variables, just like Heckman said, instrumental variables does not identify the average treatment effect. It identifies the local average treatment effect. So here is the Wald. Take the ratio of Z on Y and the effect of Z on D, both of which are causal. We replace the numerator, reduced form, with that potential outcomes notation, and we change the denominator, okay? We change the denominator to be this causal effect of the instrument on schooling, all right? And with monotonicity, this cannot be a negative number. It's got to be, well, there are a group of people. We're going to rule out the negative numbers, and we're going to say that the only thing, since you can't divide by 0, the only thing that we are going to be taking the average of is for someone that goes into the military if they are drafted, but had they not gone into the military, they would not have, sorry, D1 would have to be 1 and D0 would have to be 0. And what that means is when D1 equals 1, it means that a person served in the military when drafted, but D equals 0 equals 0. Had they not been drafted, they would not have served. Okay? They would not have served. So that means that the only persons that you are identifying average effects for, which is right here, that's an average treatment effect. Who are you getting it for? For the people that only got in the military because they were drafted. All right? So that's called the local average treatment effect, because the local average treatment effect is different from the average treatment effect, because the average treatment effect is the effect of military service on everybody. Even those people that avoided the draft, and even those people that are like, you know, patriots, and even those people that are defiers. What the average treatment effect would be like the effect for everybody. But this group right here is like, say, all right, well, it's only going to be that one population. The one population that enrolls in the military only if and only if they are drafted. And that is an average effect for one type of group. There's 4 different kinds of subpopulations, and this was defined in the Angrist, Embens, and Rubin 1996 JASA. They were all given kind of names, all right? Always takers, okay? This is what an always taker is. An always taker always serves in the military, regardless of what their instrument is. So here is a situation. My family, my dad served in the military. This isn't true, but like my dad served in the military. My granddad served in World War II. My great-granddad served in World War I. My great-great-granddad served in, you know, whatever. It's like going all the way back, like as far as I go. And my family always shows up. We always serve in the military. I come from a military family. I don't care if I'm drafted, right? That's called an always taker. They always take the treatment, right? If you're an always taker, D1 equals D0 equals 1, right? D1 equals 1. If you're drafted, you serve. D0 equals 1. If you're drafted, if you're not drafted, you still serve. Well, if that's the case, D1 minus D0 equals 0, right? Equals 0. And we said right here, the IV does not identify the treatment effect for anyone whose potential treatment, you know, whose causal effect in the first stage is 0. We rule that guy out. Here we have the never takers. The never takers. And the never takers are people that under no scenario are going to serve. Right? So D1 equals 0. D0 equals 0. So this means if I'm drafted, I will not serve. If I am not drafted, I will not serve. So maybe they have a medical condition. So, you know, if they're drafted, they got a medical condition, they're made exempt. And if they're not drafted, well, they're not going to serve. So that is D1 minus D0 equals 0. Does not identify the effect for them. When I am drafted, I dodge. Had I not been drafted, I would have served. So that would be D1 equals 0, D0 equal 1, D1 minus D0 equals 0 minus 1 equals -1. Monotonicity, if you assume monotonicity, you are assuming defiers don't exist. That's required. Until very recently, there were not really any credible tests for it. There is a new test for it. So, so that's that one. But it only is a test in a particular scenario. All right, so then compliers. I only enrolled in the military because I was drafted. Otherwise, I wouldn't have served. So you would say D1 equal 1, D0 equals 0, D1 minus D0 equals 1 minus 0 equals 1. And that's who The average treatment effect is 4. The average treatment, the local average treatment effect, the late is the average treatment effect for the complier subpopulation or compliers. You'll hear it called that. It's only the average treatment effect for the compliers. You're not estimating the average treatment effect for the patriots, always takers, for the conscientious objector, the never takers, or for the defiers, even though those 3 people have treatment effects. You could stop a patriot from serving in the military. You could force a conscientious objector to serve in the military. So they all have treatment effects. You are not identifying. And this is what Embens meant when he said, you know, we said, you know, we weren't saying that the local average treatment effect was important. We were just saying that's what you get. Instrumental variables identifies the local average treatment effect. Okay. All right. All right. So real quick, I got 10 minutes. So let's look at some practical advice. I have applications, but I'm not going to do them. So some practical advice. Let's talk about the pictures. It is very easy for causal inference to be a black box to people. Black boxes, for those that are not from the United States, black boxes are in our airplanes when an airplane crashes, but black box in general kind of means like, I don't know how this is working. It's a mystery. Like my car is a bit of a black box. I really do not understand. When I open the engine, when I open up the hood and I look at my car engine, it's got so many things in it. I don't really understand. It's got stuff I've never seen in cars before. So it's a mystery. My television is a black box. My artificial intelligence, the large language models, ChatGPT. It is a mystery to me how ChatGPT is so conversant. I could read all these papers. I still do not understand it. I don't see how it's possible. All right. So to a lot of people, that's what causal inference is. That's really the challenge, you know, is to like help people believe the results, because causal inference at the end of the day is more about beliefs than anything else. How can I help a person believe these results is kind of just as important, or it's also important part of, you know, whether or not you should believe it. Okay. So, you know, whether or not you should believe it is kind of what Angrist was saying, which is, you know, work that goes into helping people, you know, have proper beliefs is not just good methods, but, you know, it's taking the time to communicate what you've done well. So, if you don't take it out of this like mysterious box that it's in, and help, you know, show people why they should believe it, and like walk them up to it, they're not going to believe it. Doesn't matter how nice they are. They're not going to believe it. You need to change their mind. Okay. So there is evidence that IV papers show signs of publication bias with a large spike in p-values at 0.05. Doesn't show up for regression discontinuity design, doesn't show up for RCTs. So the pictures are crucial, but it's particular kinds of pictures that you're going to need to show for IV that I want to emphasize. So like I said, my opinion is, and I've had other people confirm this for me, that this is their opinion too. You want to show the walled quantities, numerator, denominator. First stage, reduced form. You want to show the relationship between the Z and the treatment. You want to show the relationship between the instrument and the outcome. So let me give you a paper of mine. There's my JHR. But let me put this one in. All right, so I'm gonna click on it and I'll upload it in a little bit. So this is a paper I did with Keith Finley, who's now at the census. And it was called Parental Substance Use and Foster Care. Foster care, for those not in the United States, is a government agency, I guess that you would call it that will remove children from their parents' home and put them in a different home. And it's done usually because of very, very, very problematic parenting. So this is parental drug use, essentially, but it's more specific than that. It's about methamphetamine and foster care. So let me read it. Foster care caseloads have nearly doubled over the last 3 decades. Parental methamphetamine use grew significantly during the same period. While child welfare workers and law enforcement claim that parental meth use contributes to foster care growth, the evidence for a causal effect has not been determined. This paper presents the first evidence of a causal effect of meth on foster care admissions using 2 exogenous supply-side interventions in meth markets from the late 90s. First, we identified that restrictions on meth precursor distribution caused meth use to decline 4.1%. Second, using 2-stage least squares, we estimate a positive elasticity of foster care cases with respect to meth use of 1.54. So basically, we're going to use 2-stage least squares, and we're going to show that meth, this instrument that we're going to use, led to an increase in we're going to argue it led to caused an increase in meth, caused a decrease in meth, and also caused a decrease in foster care. All right, so let me show you what we did. First, here's the setup. Okay, here's the background. 1990, so methamphetamine, D-methamphetamine, it's a particular form of meth. D-methamphetamine is highly toxic synthetic drug, and it's synthesized from one of 2 chemicals, or what's called precursors. One called ephedrine, 2 called pseudoephedrine, or I call it pseudoephedrine because I actually don't know how it's pronounced, and I've only can spell it, but it's Sudafed, the over-the-counter cold medicate. Well, it's no longer over the counter, but the over the counter Sudafed that has active ingredient pseudoephedrine. It's cold medicine. Okay. It's used to make cold medicines, but if you do a particular manipulation of it, it can produce meth, and it's highly addictive and problematic. All right. So what we did was we got 3 core data sets from it. Well, let me back up. In 1995, there was a government agency that handles it's like the police for the drugs. It's called the Drug Enforcement Administration, or Drug Enforcement Agency, DEA. DEA went to Congress and presented evidence and argued persuasively that ephedrine, that meth was rising, and that something needed to be done. And what needed to be done was to regulate the ephedrine wholesale markets. And specifically, it was pretty low. I can't remember exactly. It was like a lot of it was paperwork tracking who was purchasing these bulk ephedrine. It's just powder bulk ephedrine. Who was purchasing it? Because there was a lot of basically fake firms in the United States that was buying them, and they were drug dealers. But they only managed to get Congress to agree to regulate ephedrine. They did not get Congress to agree to regulate pseudoephedrine. And pseudoephedrine is a perfect substitute for ephedrine. So anything you do with ephedrine, you could do it with pseudoephedrine. They're nearly identical. And so they left a loophole in the law. And they had to close the loophole about 2 years later in 97. And then they did. All right. So what is this? This is the price of meth. Me and Keith sent in a Freedom of Information request. Yeah, that started more recently though, but this was in the mid-90s. So we sent in a Freedom of Information request to the DEA requesting all undercover police officer and everybody, FBI, anybody, DEA, all undercover purchases of all drugs going back to the 80s. It's a massive data set. You can get it too. It's called STRIDE, System for the Retrieval of Drug Evidence. Okay. It's called STRIDE. and you get all this detailed information about every single purchase, including the name of the drug, the price they paid, the potency, and the purity. We reconstructed a time series of the purity of the expected retail price of a pure gram of meth, cocaine, and heroin, right? And what we found was that when there is a gigantic spike in the price of a pure gram of methamphetamine, D-meth. This right here, it was late 1995 when Congress actually passed the law. But we identified using like a series of fixed effects, month fixed effects, we identified the exact like month where the price of meth was statistically different from its median price before. And then we kind of scaled it. Everything's scaled by that. And so it doesn't actually show up as statistically significant for some reason. You know, you can see it rising, but it's a couple of months afterwards. It increases for about, I think it was 9 months. The retail price of a pure gram was 450% over its like baseline price, and then it settles back down. Then in 97, they do it again with the pseudoephedrine, and it doesn't go up as much, but it goes up about 250, 300%, and it drifts back down. And I have a new paper on this talking about all of the reasons that it never stays up, but I'm not going to get into that here. So here's what we do. We present our instrument, okay? We present what our instrument looks like so that you look at it and you go, yeah, there's a big increase. Now, you know, I was lucky. Keith Finley is one of these people who dresses really well, who has a very good sense of style. He's one of these data science kind of types that can make any picture, sees it in his head. He could figure this out. I couldn't quite have visualized this. And he makes beautiful figures too. I know, Ronald, we actually have another paper, and we do not find evidence that cocaine is a substitute or heroin, but the reason is probably a little more complicated than it sounds. Methamphetamine was really popular in the rural counties, Pacific Northwest, West Coast, and it looks like the cocaine markets were a little thinner in those areas, and it was less common in urban areas, the South or the Northeast or the East Coast. Meth wasn't as popular, but that's where cocaine was. So it's not really obvious, even though we don't find substitution. It's not really obvious that it might not be a substitute. It's just that, like, when the price of meth was going up, it was kind of like the market for meth was not spread over the whole country. It's not trying to get into it all, but it doesn't, there's no relationship though. Here's the point. There is no relationship between whatever they're doing, you know, at Congress level. It doesn't appear to have anything to do with coke or heroin. But it definitely has an effect here, and it definitely has an effect there. That is not the first stage. That is not the reduced form, but that is probably not a bad idea if you can if you've got something that you're going to use. See, our instrument's going to be, it's going to be outside the instrument. It's going to be a variable that's equal to 0. And then in the months where the supply intersection is happening, we're going to let the instrument be the price. Okay. So we're going to be using variation in the price, but it's only like the variation that's coming from the intervention. This is probably one of the weaker parts of the paper. I mean, I've always wondered, I had a horrible time getting tenure. It was a nightmare. For 6 years, I felt like I had never had stress like that in my life. I found a coding error in my job market paper, and I got to revise and resubmit at the JHR, Journal of Human Resources. And when I found that coding error, it was so devastating. And because when I fixed it, the results went away that I had like believed in. I had gotten a dissertation. It's just so depressing. And I couldn't work on the dissertation. I couldn't even bring myself to work on it. And I never went back. My dissertation was on mass incarceration. I just left it. And so I was having to just work so hard on so many different projects to have this like portfolio of papers. And, you know, the way portfolios work with stocks, you know, you need to have like differing levels of risk, and some are safe. And this is the way I was thought anyway, is like some are safe and some are high risk. Well, my tenure work was on, none of it was safe. It was on the economics of sex work, the economics of drug policy, and then abortion policy. And so, you know, it was like, I ended up sending this paper to a journal called Economic Inquiry. I was so panicked. And I've always thought this is a fantastic paper, a paper very similar to it that looked at crime, that I think this paper is maybe potentially better at. That paper that looked at crime got into the American Economic Review. And I just could not bring myself to take the risk of shopping it around because I really needed hits. You know, tenure track is required. I saw this video the other day of these snipers, and they had to like sit there looking out their rifles while a sergeant shot a handgun right at their ear. And if they flinched, they like lost points. And if you didn't flinch, you had to stay there. I've always felt that is how tenure track was. It is very difficult. You're supposed to graduate with 3 chapters that are publication ready, or at least potentially could get published. To start over is really, I'm getting depressed just thinking about it. It was just like, you know, to start over is hard. And you just, you know, that's why your dissertation chapters need to be correct. They need to be well written. And you know, they just need to be something that you're gonna have to be working on, but you're not like starting over. I barely made it. I came in under the wire. All my best stuff came in after I got tenure. That's when I kind of went on a streak. But before tenure, it was rough. And so anyway, paper did not publish as well. I never sent it anywhere. So anyway, IV advice, picture the first stage. So here's the first stage. Remember what the first stage is. First stage, covariance YZ. So what would that be? Covariance, meth, you know, precursor, control. All right. That's what it would be. So we had to figure out a way to show a correlation between the treatment variable, which was meth use, and the intervention, which, because we had this weird instrument, how are we going to do it? So we decided to continue to use the time series and use dashed lines for the 2 interventions. But notice what we're not doing. We're not putting the instrument on it. We're just illustrating the areas of it. Because if we had sort of put on, you know, you can imagine I had put this on top of this, it would have been very hard. So what we did instead was we put a time series plot for meth, cocaine, heroin, and meth again. Now, to Ronald's point, this second intervention, you do see an increase in cocaine. It just ends up not being robust when we do the regressions. All right, but it is kind of there. But all right, so look, so what do you see? So here's what we basically think that we're seeing. So meth is rising. Intervention comes in. When the intervention comes in, prices skyrocket. It is very expensive to buy meth. And then meth treatment admissions, people going in for treatment for meth, begins to fall. Goes from about 9,000 nationally to about maybe like, you know, 7,500. It's not, you know, about 1,500, but it's, you know, every period, you know, so at peak of that every single period. So it's going down. Then the intervention stops. Basically, the reason the intervention stops is because Even though the intervention is still going on, all the drug dealers switch over to pseudoephedrine. The DEA said they've started finding pseudoephedrine at the drug labs almost very, very quickly, because it went from basically 2% of all drug dealers using pseudo to it's like 100 within a year. So they switch, and pseudo is being unregulated, and they're having trouble. The DEA is having trouble getting pseudo re-regulated, because the reason is because the pharmaceutical lobby was very, very influential in stopping this stuff from getting regulated. So it starts to rise again, goes back on trend. They regulate it, falls. Not as much, especially given this right here, but you can definitely see a break from trend, right? And then the meth prices kind of stabilize a little bit, but you know, meth kind of stays the same. Then we looked at self-admission, people admitting themselves into meth into treatment for meth versus a judge. And when we looked at the effect on judges sending people to treatment for meth, there was no change. It was just coming from people who were just not showing up to the treatment facilities because of meth. They were showing up because of, maybe they're showing up because of other stuff, but not meth. Then we look at the effect on cocaine. No effect on cocaine. No effect on cocaine prices. No effect on cocaine admissions. No effect on heroin prices. No effect on heroin admissions. These are called falsifications. And falsifications is like a way for you to kind of build the argument that exclusion might be true. Because you can imagine if there is some kind of change in broad drug policy, right? Some kind of change in drug policy. Government's going to subsidize treatment. Government's going to end up, hiring more police to combat drugs. They're going to, put people in prison for drugs. Well, you would think it would affect everything. But whatever's going on, it's not affecting everything. It's only affecting the groups that are being regulated. Okay? So then we look at foster care. Now remember, this is the reduced form. And the reduced form is covariance YZ, which would be covariance, foster care, and the precursor control. All right? Precursor control, which is only working during the window. And look what we found. Foster care, drifting down, plummets. During the intervention, and look what it then does. Rises. The intervention happens again. Now, technically, I mean, it's kind of the, there is technically, actually, I mean, the intervention does hit in December of 97, but we can't find evidence of a statistical relationship with prices here. But if you look back, you're seeing meth prices rise even before. We just don't pick it up. But you see it here, and look, that's exactly when it rises, or that's when exactly it starts to drift down. So falls, goes back up. And do you see how, like, having all of this, right? Seeing it first actually allows somebody to go into this paper here, and you can see the coefficients here. And this is what's kind of wild. Look, when we estimate the OLS model, there's actually no relationship between people going in for meth and foster care. But when you use two-stage least squares, 1.54, back then, the F statistic only needed to be 10, 17.6. It'd be nice to report Anderson-Rubens, but 1.54, it's log on log, it's an elasticity of 1.5. 10% increase in meth causes a 15% increase in foster care. Then we try to figure out the channel. right? But if all you did was report this, we got the first stage here, all right? First stage price deviation instrument. There's our first stage. We put our F statistic there. I actually think we used to report the Anderson-Rubin test statistic now that I'm thinking about that. And no, we think OLS is biased. OLS is regressing foster care onto meth, but meth is not random. Okay? It's not random. So OLS is biased, is what we're arguing. OLS is biased. So it's a biased estimate of the average treatment effect. So it's the ordinary least squares model. Okay? But this is two-stage least squares. So then we try to figure out the mechanism. Why is it that there is a relationship between meth use and foster care? Well, our data set gives us the pathways into foster care. Your parents were incarcerated, and that's why you were removed. That's not it. We find no relationship between parental methamphetamine use and foster care coming through parental incarceration, but we do find evidence for it coming through child neglect with a bigger first stage. Actually, this one's a bigger first stage. No relationship between parental drug use, actually, weirdly enough, but we do find an effect through the physical abuse channel and elasticity 1.5. It's the whole thing. And this is the other thing too. Tables. You need to be really careful about these tables. I think it's a good idea to put your I can send it to you, but back then it wasn't required and we haven't ever done it. But if you want to see it, I can send it to you. I think. I can definitely send the do file. I think I might be able to share the data. I'll ask Keith. Because I can't remember if we signed something, but I can definitely share the OLS model. Or the do file. So I always think it's a good idea to report the OLS. I remember having a conversation with Keith and he was like, I was like, do we want to report the OLS? He was like, well, you're saying OLS is biased, so you better report it. So I was like, okay. So we put the OLS model in there. All right. With heterogeneity, it's not as informative as IV. Reduced form also is a good idea. We don't put the reduced form in here. Reduced form is very common. I don't do it I never do it, but reduced form would be to regress, but I do think it's a good idea to run the reduced form. The reduced form would be foster care regressed onto the instrument and report that, because I think it is very helpful for you to see what that relationship is. But I do think you need to show the first stage. And so we show the first stage down here. Okay. We showed the first stage down here. So this was meth regressed onto the instrument. We put it down here. My desire is to make beautiful tables. And I can give you the do file for making this table too. So it does it automatically and spits it out in LaTeX. Put your weak instrument tests in there. So right now, the only thing we put was the F statistic, and it's the old one because this paper was published, I think, in 2012. And then you put in your IV model, which is two-stage least squares. The way we did it over here in my new JHR was we had two-stage least squares, IV lasso, OLS, Anderson-Rubin in here, but the F statistic up here. Our first stage results back here. Because it's just like, not always easy to do. So you have to find a way to make a beautiful table. So I can give you the code that'll make this. All right. So let me kind of end here. In conclusion, Archimedes said, with a long enough lever, I can move the world. With a good enough instrument, you can identify a causal effect. Okay. Even outside the lab, it is, though, technically the local average treatment effect. You need to know what to look for. So you got to keep that DAG in mind. Write it down. Draw it. Draw that DAG. Write it on your wall. Okay. Just look at it. Just always think. That's what I got to be thinking about. What's a random shock that is randomizing the treatment? could that thing directly affect the outcome? Could it be related to the confounder? Learn to think in terms of treatment assignment, and you will go very far. Think in terms of the treatment assignment mechanism. Yes. If you have heteroscedasticity, then you need to adjust for that because you'll over reject. So that's the thing you want to be thinking about. Don't just think in terms of the DAG. Well, like it comes from the fact that it's like probably, well, all that you technically need, Ollie, actually, all you technically need is this. That the treatment is independent of potential treatment status, potential outcomes. Okay, so we're just saying that the reasons that this was done here, the precursor control, had nothing to do with whether or not a person wanted to use meth, because that's what this would be. This is like D1 is your meth use if you were assigned the high prices, and meth use if you were assigned the low prices. So it's not like it's happening for any reasons that's related to the causal effects. It's not happening for any reasons that's related to the potential foster care. So you say that's random because physical randomness definitely ensures it, but probably other assignments could do it too. All right. But that's what you want to be thinking about. Just be thinking about that. That's the reason this natural experiment stuff got done, is because natural experiments started to look for things that assigned the treatment for reasons that were independent of these like otherwise determinants of the outcome. Okay. If you get that in your bones, you will find the instruments. You can think always in terms of treatment assignment mechanism and not models. Think in terms of treatment assignment mechanisms. You'll know what models to use. We knew to use IV lasso, and we knew to use two-stage least squares. And so we definitely think in terms of models when it's time to model. But if we did not feel confident in the treatment assignment mechanism coming from looking at this, randomized clinicians, well, then you would never go this route. You can't just say, I want to use two-stage least squares. You use two-stage least squares when the identifying assumptions hold it only, okay? So you need to know what to look for. And just like selection on observables, you need the plausible assumptions. You need properly measured data, and then you have to have the estimators. All right. Okay, so let's take a 15-minute break. We'll come back at 20 minutes on the hour. Okay, so now we are in the home stretch of RD, and we're going to go here. Slides. We're going to go here to RDD. All right. And probably I'm not going to do nearly the same amount of storytelling that I usually do. What we're going to be doing here is I'm going to try to get to a replication. I'm not going to cover fuzzy or close selection. I'm going to probably go more quickly into some basics about the identification, and then estimation using regression, non-parametrics, and then tests for violation, and then really kind of emphasize data visualization, and then we're going to do this replication together. Okay. So, all right, let's get started. Basic background. Very popular method, viewed as one of the more credible of the design-based methods, partly because of the visuals. There's something about the visuals that really helps people a lot. So we're going to kind of talk about it, but it's not immune to assumptions at all. So you still have to make assumptions. So let's look at it. RD was born in 1959. Donald Campbell, an educational psychologist, invented it, but it did not get brought into economics really until Josh Angrist. and Victor Levy wrote a paper. Although there is like a little bit of some activity here, that might be Josh Angress' paper because it gets published the next year, but it's NPR working paper. But looks like there's a little bit of a lift off here, 95, 96. There's something came out in 96, a couple more. These are still tiny though. All right. So you remember how much IV was? It was 0.3. So it's like IV was way up here. RD at its top is about 10% of all working papers in this one prestigious working paper series, and it's about 7% of all papers in the top 5. It's very hard to do RD because it's very hard to find good RD situations. It's become very popular ever since 1999, which is when Sandy Black, and Vint Angerson Levy published their papers that used RD. At that point, it is just skyrocketed. So what we're going to do is we're going to estimate some causal effect of a treatment on some. If you kind of think about what we've done, actually, let me put this up here. So when you think about the treatment assignment mechanisms that we've looked at so far, number one was rationality, right? Worst case scenario. This was the perfect doctor. Perfect doctor is a treatment assignment mechanism. And when you have this kind of Roy model sorting into the treatment, it's very hard to, it's very hard. Okay. Those are going to be the hardest of all of the causal problems. And you typically are going to see it with high stakes treatments where individuals choose their own treatments. Those are probably, and especially if it's adults or if it's firms, those are going to be harder. You're going to need an instrument. Secondly is covariance or propensity scores. Okay, this is the unconfoundedness assumption. Covariates are assigning it, and within the covariates, all remaining variation is random. Third is instruments. Oh, I should have had this, sorry. 2, randomization. You know, best case scenario. Okay. 3, 4. Instruments, you know, only identifies late. Only ATE. ATE or ATT or ATU, depending on assumption. Okay. So, you know, you get all these like assignment mechanisms that have various sources of randomization in them. And depending on the sources of the randomization and the power of that randomization to operate on units, you have the ability to pull out or estimate different, you know, different versions of these aggregate parameters. Okay. What we're going to do is we're going to get a fifth. And the fifth is going to be a running variable that will assign the treatment. And it will hold under something called smoothness. All right, we had 5 assumptions up there. So smoothness, and you'll estimate an average treatment effect around a cutoff. That's what you're going to get. So it's still going to be an average treatment effect, but it's going to be very local. It's going to be very local. And we're going to look at a situation where there's like perfect compliance, and then it'll be like average treatment effect there. And then we're going to, when then we look at, well, they're all the same thing. The ATE and the ATT and the ATU are all identical in the RCT. So, you know, in the RCT, all of those parameters are the same thing. So you could say that it's the ATT, but it's not really, it's not the same meaningful thing as when we have sorting. So we're going to be looking now at this, like, you know, running variable. And that's what we mean by the regression discontinuity design, is that we allow something called a running variable. Well, it will be the late if there is not 100% compliance, and it'll be the average treatment effect if there is. The fuzzy design that I mentioned is an IV. It's an instrument. It's an instrumental variables. So we're going to look first at this situation where it's like perfectly compliant. It's like Medicare. in the United States is an elderly insurance program. And if you're age 65, you're basically on Medicare. And if you're not age 65, you're not on Medicare. So that's like 100, basically almost 100%. Okay. So you can get on it if you're like disabled, but for the most part, excluding that, like that's, nobody gets to choose Medicare. You're just like either, yeah, it's that your age chooses it. Okay. So it's again kind of the idea. Okay. The idea here is that in this situation, the person is choosing it. And in all of these situations, something else is choosing it. Okay. Something else is choosing it. Outside choice of treatment. And this is like person chooses own treatment. And so, you know, that's why, like, you know, when you have that, covariates are doing it. You would think a person is choosing it themselves. But see, that's the idea that we learned with unconfoundedness, is that it actually, unconfoundedness is saying no. That unconfoundedness is saying no. The person is never choosing to get divorced. They're never choosing to get divorced. Rather, their covariates are choosing it. But if you look at a group of people that have the identical covariates, then they're not choosing it. It's getting chosen for them through randomization. See what I mean? So when you frame it that way, you kind of go, "Whoa, when is that going to happen?" So, but that's the idea. That's the idea. So we want to estimate some causal effect of a treatment on some outcome. We cannot just simply compare two groups because of the self-selection. But what if the treatment was forced on units because someone is using a variable that takes on different values? They split the sample, and if you have a number above it, then you get treated. If you have a number below it, you don't get treated. When I was first working on that paper that I was just showing you, when I was just first working on this one here, the mental health paper. Well, local average treatment effect is about compliers. So this is going to be the average. If you look back where I said it's the average treatment effect around the cutoff. It's not the local average treatment effect around the cutoff. It's the average effect for all those people on the left and right hand side of the cutoff. You're going to be estimating the average treatment effect, assuming you have all of them. Assuming you have 100% compliance. And if you don't have 100% compliance, which you sometimes do not, then it will be a local average treatment effect around the cutoff. So it is still local. You are right. You are right, Shivangi. It is local, but it doesn't have the same, like, it's not called late. It's more like a slice of the average treatment effect, which is not, it's not about compliers. It's not the average effect of the compliers, is what I mean. Okay. When we first started doing this study, I thought I had an RD because they told me that if you get a 0, they said there's a score. There's a score. If you get this like number on a score, if the number's above a threshold, then you'll get assigned to the mental health court. Otherwise, you won't. You'll get a high mental illness score or a low one. And I thought for sure. But the problem was that it was a number that took on 4 values. And so it wasn't like rich enough. So you typically need like a lot of numbers. You typically need a lot of numbers. And I'll explain why that is in a minute. So, but what RD is going to do is it's going to formalize it. All right. So let's look at this picture. All right. So this is a picture. The RD is really data intensive. I mean, the covariate stuff does not really do a lot of pictures that I can think of. RCTs have these simple histograms, but the IV has its own data visualization and RD has its own data visualization. Diff and diff has its own data visualization, and so does synth. And RDs looks like this. RD is always going to be this variable that we've been talking about that assigns the treatment. Here it's age, okay? And then it's going to be that like either the outcome or the treatment, all right? So here we have a treatment variable, all right? And here we have age. Now in the United States, this is for those that don't live in the United States. In the United States, when you turn 21 years old, it is legal for you to drink alcohol. But if you are not 21 yet, it is illegal to drink alcohol. But, you know, lots of kids drink alcohol. My first time I drank alcohol, I was 16. And then many people, even after age 21, won't drink alcohol. For Latter-day Saints, Mormons, it's against their religious principles to drink alcohol. Muslims, as I understand it, it's against their religious principles to drink alcohol. Doesn't matter how old they are, doesn't matter where they live. Okay, so there are situations where you will have this conversation I was having with Shupangi, which is you can have non-compliance. You can have a group of people that are drinking alcohol before age 21, and you can have a group of people that refuse to ever drink alcohol. So you can have these always takers, never takers, in which case you're going to only be estimating lates, all right? But let's put that aside for a second. All right, so look, here's what we have. We have a couple of things I want you to see. One is that we got these dots. See that? Those dots. So I'm going to tell you what those dots are in just a second. Second, we got a line. And if you look close, the line is curved. It's not a straight line. All right, it's not a straight line. It's a little curved. And then notice that the line is different, is not connected. Over here, it's connected for some reason. It's smooth over here, but it jumps here, which must mean that you've like you draw the line here, you lift your pen, and then you draw it over here. Okay. All right. So what these are different measurements of drinking. So one is, what percent of days are you drinking a lot? What percent of days are you drinking a lot? So on these days, at these ages, what percent of days are you drinking a lot? And it's about 2%, goes up a little bit, maybe to 3. But then when they turn 21, there's a little bit of a jump, and it goes from about 3 to 4%. It's definitely pretty large if you look at proportions of days drinking, not just heavy drinking. Heavy drinking is not as common, but there's a bit of a jump there. Looks like it goes from 8% to 10, a little bit over 10%, like maybe 11, maybe goes up 3 percentage points. And then right here, drinks per day, not as big, not as big. Okay, right here. Yeah, it goes from like basically 4 to like 4.1. So the number of drinks they have per day isn't going up, but the number of days they drink is going up. Okay. All right. So what is the dots? The dots. All right. So first of all, the x-axis is age, and that's called the running variable or selection variable. The running variable is determining whether or not a person will be exposed to the treatment. All right. And then there is a cutoff, right? The cutoff is the minimum score on the running variable when a person qualifies for the treatment. And here it was age 21. At age 21, you qualify for the treatment. Anything above age 21, you just remain treated. So technically, it's like you're being treated here with something, and you're not being treated over here. Yes, it's got multi-valued or continuous. It can be multi-valued. But if it is multi-valued, you're going to need a lot of them. You're going to need a lot of them. So then you got cutoff. Then what you have is the lines, and they're curvy. These are OLS fits fitted values of the data. Okay, OLS fitted values of the raw data, and it's curved because we are allowing a flexible polynomial specification of the OLS model. You're going to be basically doing this. Y regressed onto, outcome or variable regressed onto a constant plus age, B1 age plus B2 age squared plus error. Once you get those fitted values, you're going to get the fitted values of the outcome, and that's what this is. That's the fitted values of the outcome, okay? And then the last is the dots, or here it's X's, the dots. These are averages of the variable on y-axis for a given small bin. Here it would be like, probably month. So it'd be like the average amount of drinking in that when you're that age. Classified at a very kind of tight level. All right. Here you have another picture. All right. This is the outcome. All right. Here's the outcome. And notice here, there's a bit of a strangeness principle to this RD stuff too. Here it's kind of like first stage stuff. This is drinking. Here it's like outcome. Right? And notice what goes on. Here we have alcohol-related deaths. That's down here. Then it goes drug-related deaths. Then it goes external other, suicide, homicide, motor vehicle accidents. Now look, none of these, they're like placebos. None of these have a jump. Right here, there is a big jump. And is statistically significant and is detectable. So the number, the death rate from driving, it's just a driving accident, the death rates from driving jump at age 21, which is also when it is legal for you to drink, and it is also when we see some evidence of drinking jump. We don't see evidence. It's kind of bounces around a little bit, but there's a discrete jump that happens right there. That gap at the cutoff is an estimate of the average causal effect of the intervention on the variable, but only at the cutoff. Which here means at age 21, the average effect of legal drinking age is a five additional deaths per 100,000, but only for 21-year-olds. Only for 21-year-olds. And only for the 21-year-old compliers, right? Only for the 21-year-old compliers. And those are like the elements of an RD figure. You have running variable, some sort of display as the cutoff. A lot of people don't like to put some people will put, they'll put a line there, but a lot of people object to doing this kind of thing. Here it'll be a late. Here it will be a late. Yeah. Here it's going to be late, Anna. Because we know it's going to be late because not everybody starts drinking. And not everybody was abstaining over here, and not everybody starts drinking. That's how you know it's a late, because we're only going to be estimating, in this example, we're only going to be estimating the average treatment effect at age 21 for those people who only started drinking because it was legal. People like me that were drinking from the age of 16, I'm not necessarily, I might be well, I might be a part of this because I might start drinking more, which I did start drinking more and started drinking out, like at bars and stuff where you have to drive. So that could happen. But point is, it's like, it's only going to be those people. It's only gonna be those people. A lot of people will put, a line there, but there's a lot of principled opposition. Exactly. That's right, Sheva. Yeah, we haven't got that language yet, but that's exactly right. Okay. So rather than cover examples at the end, I'm going to do them I'm going to skip the examples. So I'm going to go right here. So we're going to go into this RD language, right? So keep in mind, RD is a method of mimicking the experimental design as opposed to merely a regression model. There's a lot of new terms, tons of weird pictures, tons of weird concepts. So running variable, it's usually continuous, like Miguel was saying, or it can be multi-valued. My project, it wasn't multi-valued enough. Only having 4 was not really going to allow me to deal with the problems. That's why I went in the direction of instruments. And then I actually kind of decided not to study the courts. I decided to look inside the jail before they ever leave the jail. So running variable, usually a continuous score that some firm or agency is using to assign treatments to units. Trends, it's not time trends, it's trends in the outcome. See how there's trends in the outcome? This is not trends over time. This is trends across the running variable. The cutoff can be seen as an instrument, not X. The cutoff can. Yeah, it is. Ben Scatter has come in pretty strong on this stuff. I have some code with Ben Scatter, but so we have trends, cutoff, it's a particular value at a point on the running variable above which a firm gets treated, and then a discontinuity or a jump. We're estimating breaks in the outcome of interest right at the cutoff. And when we say that happens, we say there is a discontinuity. Okay. And then there's regression. Most of the models are simple differences in means, local regressions from OLS, or global regressions. We're not going to get into the global regressions. We're going to go more into the local ones. All right. Sharp versus fuzzy. Sharp versus fuzzy. So there are 2 kinds of RD designs, which was just brought up. What is it? Who said the sharp? Oh yeah, Shubhangi says sharp versus fuzzy. What is that? This is a sharp design. Sharp designs are like Medicare in the United States, which you are literally not able to get on Medicare, minus being disabled. You're not able to get on Medicare until you are age 65, at which point you are put on Medicare, right? So 65 and older year olds are on Medicare. You can look at them. You can look at a person, and if you just know their name, you know if they're on the treatment or not, okay? Versus fuzzy. Now, it kind of depends on what you're identifying with that alcohol study. If you're identifying the effect of the minimum drinking age, then the minimum drinking age, everybody's treated, I guess you could think of it like that. But let's just imagine, though, we're talking about it different. We're looking at the effect of alcohol. We're looking at the effect of alcohol. If I know your age, I might know all of y'all's age, and I can't say with certainty I know that you drank. I'd have to have more data. And even then, all I could say is probabilistically, without knowing anything about your private patterns. I could just say, well, Julietta is like 26. And if I go into survey data, about, 65% of all 26-year-olds drink alcohol. So I look at Julietta, she's 26 years old, and I say, well, Julietta is 26 years old. There's a 65% probability, 65% chance that Julietta drinks alcohol. Okay. And that's called a fuzzy, because what fuzzy means is that the conditional probability, well, fuzzy designs mean, yeah, there were people that were drinking before the cutoff, but there's going to be a discrete jump in the probability of drinking. Maybe it goes from 30% to 60%. Okay. So there's these issues with RD. One of them is there's no common support, well, at least with the Sharp design. With so like with Medicare, all right? With Medicare, there's no common support. What does that mean? That means that if you're 66 years old, there are no 66-year-olds in the control group. And if you're 64-year-olds, there is no 64-year-olds in the treatment group. Common support remembers that there is a non-zero probability of being in the treatment group and the control group for a lot across the running variable. And with a Sharp design, you have no support. You have no common support. And it's pretty extreme too. So extrapolation is also the second thing. Since you don't have common support, and you don't have randomization within the running variable, that's the other thing. So you could in the fuzzy situation have common support, but you don't want to compare drinkers and non-drinkers of the same age because you know they're choosing their alcohol. Instead, what you're wanting to do is you're wanting to leverage the treatment assignment mechanism, which is the running variable. And so what you're going to do is you're not going to estimate like a treatment effect here or a treatment effect here. You're going to use this data on the left side and use this data on the right side, and you're basically going to be extrapolating from a trend so that you can kind of get an estimate over here and then just do a comparison. And that's what OLS does. OLS uses the functional form that you've imposed on the model or on the specification, and then extrapolates beyond the support of the data. That's its power. OLS will extrapolate, okay? But that gets into things like trends, modeling the polynomials, how large the bandwidths are, and the number of observations within the bandwidth. So there's all these like little bitty details that you have to deal with in RD, and that's where I want to spend a lot of our time. And then there's the treatment effects. We're going to be estimating average treatment effects only for the people at the cutoff, only for the compliers. And that may not be informative of any other point on the running variable. So you could study the effect of Medicare on mortality, but you would only be learning about 65-year-olds. You would never know the effect of Medicare, of universal health insurance on 85-year-olds. And you would never know the effect of universal health insurance on 35-year-olds, even though you might know it for the 65-year-olds, okay? So in the Sharp design, what we say is that the treatment assignment is Sharp, which means it's like completely determined by the running variable, because so it's like there's no rationality at all. So you've got like this, you got if you're not treated, or if your running variable is less than the cutoff, you cannot get in the treatment group. And if your running variable is above the cutoff, you are 100% exposed to the you're treated, okay? So the Sharp design creates these common support problems. You're going to extrapolate, but since you're extrapolating and you're predicting from one side of the cutoff to the other, using a fit of the data, you have to be sure to get you have to be sure that you have the right model. You have to be sure that you've got like the correct specification in it, because you're going to be using that functional form. You're going to be using that functional form with those fitted coefficients to predict outcomes. And this right here is the treatment effect. Under the Sharp design, you are going to get an average treatment effect at the cutoff, okay? At the cutoff. And so you're going to get the treatment effect at the cutoff, and that's going to be Y1 at C0 as X goes to C0, Y0 as X goes to C0. And so basically what you're going to get, no, not X, but the cutoff. This is the instrument. See, because it's not that age is not assigning alcohol drinking. Age 21 is assigning alcohol drinking. So it's a little bit different. You know, if I'm 25, you know, that's not doing it. It's the switching. You want to be thinking about the treatment switching from control to treated. And that's happening with the cutoff, which will be a dummy variable. Okay. So your treatment effect is under the sharp design is the average treatment effect, but only for those people at the cutoff. And the reason why it's only for those people at the cutoff is you're going to use all this extrapolation to extrapolate at the cutoff, even if you don't have a lot of data there. That's what you're going to be doing. You're going to be basically identifying a average causal effect for groups of units at the cutoff, even though maybe there's not very many people at the cutoff. You're going to have to use people a little bit further out to project. That's kind of the idea. You're going to be using those trends. So there's like two different things that go on in this this research design. If that happened, they have to be untreated. They have got to be untreated in order for this to work. So if they change it, they raise the minimum age from 65 to 67, then they've got to be untreated at age 66. So if you don't have anybody untreated, you may have to wait a couple of years. Can it handle selection and assignment? Well, that's what we're going to get into. There's actually two different approaches that are taken with RD. One, and I don't mention it here, but one approach is that it's as good as random, which is what you said, coin flip. It's as good as random around the cutoff. Okay. And that would not allow for any selection. The second is smoothness. And smoothness does restrict the selection. It does restrict the selection. So basically, when you have like randomization based assumptions, that's like RCTs, matching, weighting, IV. Okay, all of these use independence in some way or another. Independence, conditional independence. Independence is the within it, with the independence of the instrument. RD can do that too, but there's a paper by Hahn, Todd, and Vanderklau. And I have an interview with Petra Todd, but I have an interview with Jen Hahn at UCLA, and he talks about this paper that they wrote. And RD does not require randomization. You can do randomization, and if you assume randomization, then that will allow you to do certain things. But if you don't think you have randomization, you can still use something called smoothness. Now, what's going on here? RD restricts the behavior of Y0 in that unknown realm to simply be a smooth function of the running variable. Okay, so even though it's not observed, you're going to be assuming that expectation Y0 would not have jumped, and expectation Y1 would not have jumped. You're going to be assuming that it's smooth. Diff and diff is a restriction on Y0. That's called parallel trends. And synthetic control is a restriction on Y0. Okay? So here's the identifying assumption, which is relevant, I think, to key what you're saying, but I'm not exactly positive how to exactly explain its connection to selection. There's definitely going to be some situations that it's not going to handle it. So if you've got, but I'm not positive how to write that down. So what you're assuming is smoothness of the conditional expected potential outcome functions through the cutoff. So you're saying that there is some random variable Y0, and as the average of Y0 moves across the running variable, it would have continued to be a smooth function of the running variable had the treatment never occurred. All right. Same thing with Y1. It's continuous, it's smooth in X at C0. If population average potential outcomes are smooth functions of X, then the expected average outcomes would not have jumped at C0. Therefore, the only thing that can be explaining the jump is the causal effect, not Y0, but going from Y0 to Y1. All right. So here's an example. All right. This is potential outcomes. This is Y0, average Y1. These are all these units. And had the treatments remained turned on below the cutoff, Smoothness implied that it would just continue to be a smooth function of the running variable. Verse, and then this is Y0 here. So even if the treatment had not happened, that's what Y0 is. Even if the treatment had not happened, it would have continued to evolve smoothly. Versus actual outcomes or realized outcomes. Realized outcomes say, well, right here it's smooth, but it jumps. And the reason that it jumps is it's kind of simple. You don't observe those values. You don't observe Y0. And you also don't observe Y1 below the treatment. So you don't know that it's smooth. You have to assume it. You don't know that it's smooth. You have to assume it. The only thing you observe is the jump. You don't observe the potential outcomes. So you assume, though, that had it continued to evolve smoothly, then there would not be, because everything on here, all of these are average treatment effects, because it's Y1 minus Y0. Yeah, we're going to get into that, Eduardo. Correct. No. Smoothness, the density tests are tests of smoothness. I think let's wait and hold on that. It is not a parallel trends assumption, because look, it's not saying they're parallel. Here, let's take a break and we'll come back. I got to go get my iPad and then I'll answer Anna's question about parallel trends. So we'll come right back. Okay. All right. What was I talking about? Oh, parallel trends. All right. Right. Okay. All right. So I can see why you probably thought parallel trends, but let's make that the cutoff, C0. That's our running variable. And we'll say that's outcome. Okay. We'll call it Y1, Y0. And we're going to have these dots here. Wow, I shouldn't have done that. So whatever. And then this. Okay. So what we are saying is that this right here is this over here is expectation Y0 as a function of X. And so what we're saying is this is all actually. All right, so this right here is not observed. And this is observed. Okay. The fact that the lines touch at C0 means here smooth. the expectation function, the conditional expectation function is smooth through the cutoff. Okay. But that does not require that Y0 be parallel with Y1, because here you could have like Y1, you could have like Y1. Not observed. It's observed. Okay. And so it's also smooth. Both expectation Y0 and expectation Y1 are technically smooth through, they're smooth functions through X equal C0. Okay. But so what's different? So what's different is that like here, So what is that? Well, what is that? So that right there is expectation Y1 at X equaling like, maybe that's like, 15. Maybe that right there is 20. So that's X equal 15, 1, minus expectation Y0, X equal 15. It's an average treatment effect. Okay? It's an average treatment effect. In fact, every single one of these is an average treatment effect. It's just that right here, it's positive there, and then right here, it becomes negative. That's perfectly fine. RD, the lines, the difference in the lines is measuring, the difference in the lines is Y0, and it's met, one is Y0 and one's Y1. So parallel trends is always about treatment group, control group, Y0. This right here is this part up here, that right there is Y1 and that's Y0. So the difference between them is the average treatment effect. And so we're not requiring that the average treatment effect, we're not requiring Y1 and Y0 to be parallel at all. We're just requiring that Y0 be smooth and Y1 be smooth. Not that we're not making any statements about how they relate to each other. We're making statements about how each one relates to itself to the left and right of the cutoff. So there could be like, when you go back here, this is Y1 and Y0 are parallel. And what that means here is that average treatment effect and that average treatment effect and that average treatment, they're all the same. Okay. But what I showed a minute ago was they weren't all the same. The treatment effects were changing across the cutoff. You could imagine that universal health insurance has a different effect on 90-year-olds than it does 65-year-olds, than it does 20-year-olds. Okay? Okay, great. So, and not only that, but we are only, and actually maybe this would be helpful. Takes me a little bit of time for this Mac thing to work, but give me one sec. Okay, so what are we identifying? RD only identifies that. It only identifies the effect, the average treatment effect at the cutoff. Could be negative over here. It could be a different sign somewhere else. So in that sense, it's like, you know, this is what gives it limited external validity. This is what gives it limited external validity because it really doesn't, it does not tell you anything about these over here or there, only right there. The only way you could make the assumption, the only way that you could make the assumption is that it's universally applicable would be to limit the heterogeneity. But, you know, how the heck do you know what it is there? You don't know. You haven't done that study. So nobody knows. Nobody knows what the effect of Medicare is on super old people. And nobody knows what the effect of Medicare is on 35-year-olds or 20-year-olds, even if they know what the effect is at 65. Okay, those are different populations. They might have different potential outcomes. So smoothness is about potential outcomes. Discontinuity is about realized outcomes. And you're assuming this so that when you see the jump from here to here, you can interpret it as a causal effect. You have to assume that it would not have jumped otherwise. Okay? Smoothness justifies also the use of these regression models because these regression models use these functions and have these linear these linearity properties. So, you know, as the running variable goes up, it's going to go up by some constant that you've estimated, and it's going to do so smoothly. So if under smoothness justifies the use of OLS, but you're again going to have to deal with some specification stuff. All right, so let's look at some estimators. There's two ways to estimate the treatment effect. You can use local regressions, or you can use non-parametric kernels with local linear regressions. I'm going to kind of briefly go over the global and just go over the local, right? So okay, first thing, here we go. So let's assume that one of the first things you need to do whenever you do this project, you need to recenter your running variable, all right? Recenter it so that at the cutoff, the new running variable is equal to 0. You're going to need to do that for reasons I'm about to show you, all right? So you'll often recenter by subtracting the value of the cutoff from the running variable and having a new running variable. So it would be like age minus 21, okay? Or age minus 65 for Medicare. It does not change the interpretation on the running variable. Does not change the interpretation on any other variable. So here we have age, and I'm going to subtract 65 from age, okay? When I do that, I've got this, you know, age minus 65 multiplied by beta 1. Beta 1 gets distributed. Beta 1 times age is back. Beta 2 times education stays the same. Error term has not been modified, but I do have this new beta 1 constant times a constant. So now I got beta 0 minus beta 1 65, and I've got this new constant. That's the only thing that changes. When you recenter, only the constant changes. The slope coefficient does not change. Okay? All right. First thing is, smoothness does not mean it is going to be a straight line. Smoothness and curvy lines are not the same thing, okay? Smoothness and straight lines are not the same thing. Okay, so here we go. The use of polynomials. Okay, so if you have a nonlinear relationship of the potential outcome, you tell me in just a second, Rabbits, and I hadn't thought of that. If you think that that's what it would be, the specification is going to be a little bit unique. It's going to be the saturated regression model interacting the treatment with the running variable. Not saturated, but it's going to be interacting the treatment with the running variable and any polynomials. So you're going to have here, like, let's say you have expectation y0, and let's say that it's nonlinear. Maybe it grows, it's concave or something like that. All right, so here we go. It's going to be a reasonably smooth function of f of x. It'll be smooth, but it won't be a straight line. In that case, you'll fit a regression model that's how does y relate in a nonlinear way with the running variable, and then you'll have the treatment separate. All right, so here we go. That's with respect to y0. So what you're going to be doing is this f of x is doing all the work of reproducing y0. Because in a world where it's not treated, that'll be a 0. So you would just basically be saying, I fit my model on my data where y equal to y0. I get some fitted coefficients, and then I project what it would have been had it not been treated. Okay? You're going to be using higher order polynomials. It's pretty mechanical. You're going to be using higher order polynomials to predict. I've not seen anybody suggest using anything else. Lasso, elastic net. I've not seen anybody, but you could in principle, anytime you see someone describing using prediction, using OLS to do prediction, a lot of the time the question becomes, well, OLS overfits. And so is there a way to maybe do this better? And so that is kind of some of the stuff we're going to do, but I've not seen anybody talk about machine learning. So let me show you what happens when you have nonlinearities. All right. So if you have nonlinearities, it says saturated, but it's not saturated. So look, expectation y0. Let's say that y0 is nonlinear in x. Okay. It's got alpha. You've got it. So that's age squared, and that's going to be like age cubed. Okay. Maybe there's like some other stuff in there. You've got these coefficients that are giving slope parameters on these polynomials. And so you're going to get, like, as a result of this, you're going to get something like this. You're going to get, like here, expectation y0. Okay. As opposed to what? As opposed to this. All right. For that one, for the top one, that's just y0 a plus beta x plus e. The bottom one, it's y0 a plus b1x plus b2x squared plus b3x cubed plus ... plus e. Okay. And so all it's doing is it finds those fitted values, then it predicts y0. And since it's, has a constant slope, this is, a plus that, it's going to create a straight line, but here it's going to allow it to move. Okay. It's going to allow it to move. I don't know if I didn't do this right, but like if you've got like higher order polynomials, it can overfit. Okay. So we're going to say, all right, do that. And expectation y1 has its own relationship under heterogeneity. Expectation y1 and expectation y0 do not have to have the same shape. We saw that in my little iPad thing. It doesn't have to have the same shape. If it doesn't have the same shape, then you've got to model the potential outcomes separately. You got to find a way to give a coefficient to x at the lower levels, or a coefficient on x and a coefficient on x squared that's one thing for y0 that might be different for y1. And to do that, you have to interact the treatment with the x. And to do that, you have to take a recentering of the running variable so that when you do the interaction, the algebra will allow you to isolate just this. All right, so it's going to look like this. Here's the outcome model. This was the potential outcomes. We think there might be heterogeneity. We don't know, rather. We don't know that there isn't heterogeneity in the potential outcomes. So we're going to allow it to take on different values. To do that, you're going to say y regressed against a constant, x squared, xp, treatment variable, which is equal to 0, 1, 0 if it's below the cutoff, 1 if it's over. Then you're going to interact z with x. Sorry, d with x squared, d with xp. Okay. Now, beta 1 star is going to be the coefficient on x, but it's going to be where it is above. And then this is going to be beta 2. That's going to be on x squared, but only x squared at the higher part. But the thing is, what you're saying is that, well, there's like this fixed relationship on x squared, and wherever it is along the running variable, it's always beta 12. It's always beta 12. It's like you could have a low ages, you could have high ages, but the quadratic always moves in beta 1, 2. And you've identified it at this higher part. That's just like a typical regression. That's a typical regression. What it does is it allows for you to identify the local average treatment effect here, only at the cutoff, but allowing for all that heterogeneity, nonlinearities. So here's what you get. Here, so let me sort of show you. This person did not allow for nonlinearities. Okay? Doesn't allow for nonlinearities. So he fits lines through the data. And because there's nonlinearities in the data, when he fits a single, line, it sort of like this is kind of pulling it up, that's pulling it down. And so as a result, it hits there at the boundary. And see, remember, we're extrapolating to the boundary. We're extrapolating to the boundary. So that's the boundary. And you fit it here, that's the boundary. But you can clearly see that it's nonlinear, that this right here is just like an underfitting problem. So here we put in a quadratic. And when we put in a quadratic third order polynomial, but it was really just a quadratic. When we did that, they touched because the data generating process was nonlinear. So using polynomials is pretty common. But you have to be careful because if you use higher order polynomials that are too high, you can run into this overfitting problem. Andy Gelman and Embens, they have a 2018 article. They caution against overfitting on these regressions. And they sort of say, be careful about this overfitting on these global regressions. Maybe don't go above a quadratic. Okay, because you can end up with these higher order polynomials with these kind of crazy fitted lines, and you'll find spurious cutoffs, spurious discontinuities at the cutoff. That's really just coming from the poor performance of your kind of, hot overfit OLS model. That's really all it is. All right, so let's look at some new terms. Good. All right. So let's look at some new terms where we move away from these global regressions and we start looking at these local regressions. Now, these local regressions are the most common way that people will do this. All right. The most common way that people will do it is they'll do local regressions. And what do local regressions mean? What local regressions are going to do is they're just going to, they won't use all this data. All right. They won't use all the data. They'll just use some data kind of close. Right. They'll use some data kind of close to the cutoff. Now, the problem is the closer you get to the cutoff, you are able to kind of extrapolate, potentially like more accurately at the bandwidth, but sorry, accurately extrapolate to the boundary. But, as you kind of shrink, how much, if you go like here, okay, and it's like, what are you doing? Well, what you're doing is you're just like kind of getting rid of, you drop all that data, okay? You drop all that data. And when you do that, okay, you're just using this data and that data for all of your analysis. And you just like dropped it, okay? Now, you could, I'm going to put this away over here. So you could do that. You could do that. Or you could even, and as you do that, see, look, as you do that kind of thing, look what happens. So even with you're going to get like a better fit. See that? You're gonna get like a better fit. Now, but the problem is, as you get closer and closer, okay, as you get closer and closer to the cutoff, you do get a better fit, but you've got like a lot less data. You got like a lot less data that you're using, and so it can get very noisy. So there's like this trade-off here between like getting closer and closer to the cutoff using fewer and fewer observations, but then running out of observations. And as a result, kind of increasing the noisiness of the fitting. So with that in mind, there's some new terms we're going to look at. There's something called kernels. And what kernels are going to do are going to be weights on the observations when you run regressions near the cutoff. Bandwidth is how big the window, how many observations you're going to use, like how big that rectangle is going to be. And then bends are going to be the size of particular intervals. And all these kinds of things end up being used in different ways with this like local analysis, right? Local analysis. So least squares, what it does is it models the counterfactual, all right? It models the counterfactual using these functional forms. And these functional forms are parametric. So because they're parametric, meaning like they're following a particular regression specification, and you've got in there those quadratics and those polynomials, and so those things are predicting the outcome. They're going to have poor predictive properties on counterfactuals above and below the cutoff, especially when you have. So another way of doing it is to approximate the running variable flexibly and use a non-parametric kernel. Hahn, Todd, van der Klaauw proposed local linear non-parametric regressions, which basically became OLS with weights. And the weights were based on the bandwidth and how far away you were from the cutoff. I don't know that I've interviewed Petra and Hahn, and I just lined up the interview with van der Klaauw, Wilbert van der Klaauw. It'll be clear in just a second, Sebastian. Yeah, it's actually, I've probably not as good to just put the definitions up. But van der Klaauw, they're going to all talk about this paper. All right. So this local non-parametric regression is going to it's going to reduce the bias. And it's going to, but what's going to be nice about it? What's going to be nice about it is that you are kind of getting close, like because you start using weights, and weights are the kernels. The weights are a function that determines. Kernels are a function that will determine weights on each of the observations that you're using in your regression. That's what the kernel is going to do, okay? When you ordinarily run ordinary least squares, there is a kernel function that's determining the weights on the observations, and it's basically like treat them all the same. Sometimes I think seen it the rectangular kernel or the uniform kernel. I've seen it. I think I've heard it described both ways. Kernel, when it's like, when you don't put any like additional weights on it, it's as though you've weighted them all the same. So there's a kernel that produces that. It's the rectangular kernel. But there's other kernels. There's kernels that'll put more weight on the observations that are closer to the cutoff. And what that's going to do is, if it's closer to the cutoff, it'll kind of pivot. It'll pivot the slope coefficient by putting more weights in the regression on those observations that are almost 21 or almost 65. And those ones that are like 20 or the ones that are like 90 just get barely any weights altogether. Okay. And that means you can still have more observations in, but you're not throwing as much data out with these weights, and they're going to have certain properties that will allow for lower variance. So it's like a histogram, okay? But it's a regression with polynomial terms, because histograms, as we'll see, weight all the observations exactly the same. Polynomials, regressions with polynomials will be tilted, but you will be allowing certain observations to be more influential in that regression line than others, okay? So if you do go this route, which and I'll sort of give you an example of what to do, what I think is probably good practice. When you do go this route of these like local polynomial regressions, it changes a little bit, sort of. First is you got to decide how big this bandwidth is going to be. What does that mean? Bandwidths are like this. Okay, so you're gonna have like this data. You're gonna have this running variable X. You're gonna have this cutoff C0, and it's gonna be like, whoops. Here. Okay. And so the question, what is a bandwidth? So a bandwidth is like, it would be like you just drop those observations, or maybe you don't drop them, you just give them a weight of 0. Okay. And as a result, you only use the observations in here. And that's your bandwidth. Your bandwidth is like this would be like CO minus H. And this would be like CO plus H, and H is your bandwidth. And it's like, it doesn't have to be, the bandwidth does not have to be symmetric. And we'll look at that later. But like, you're basically just saying how far to the left, how far to the right. It's not a confidence interval. It's just like, how much data do you want to use along this running variable? All right. Once you've got the bandwidth, okay, then you're going to be running regressions off the data. All right. So there's like maybe there's like millions of observations. Okay. There might be millions of observations here. And so the question is, well, how do you want to weight them? You're going to run a regression. How do you want to weight them? Do you want these to be the same as that? In which case, you might, if you were to do just like no polynomials at all, then this would be, a histogram. That'd be your fit. But if you're going to allow for larger weights, where these get larger weights than over here, well, then it like changes. Well, shoot. Then it starts to pivot. Okay. And so the question is like, all right, here's a straight line. I'm weighting this differently now. I'm weighting them differently. All right. And here I'm making it a function of the running variable, but maybe I'm also not even putting the running variable in. I'm just simply putting more weight on these observations. Even without controlling for the running variable, that alone will pivot. Okay. And then you could say, no, I'm going to do something different. I'm going to actually allow for a quadratic. If you allow for the quadratic, then it might be something like this. Okay. So you have to make 3 decisions when you do these like local polynomial regressions. You got to go, how much data am I going to use? What kind of kernel am I going to use? Am I going to weight everything the same, or am I going to weight stuff differently? Weight observations that are larger if I go over here. And how many polynomials am I going to use? Am I going to use a quadrat? Am I going to use 1 polynomial, which would be just controlling for age? Am I going to put in 2, which would be like age squared? Or do I put in like 10? Okay. So you have a broad set of writings and suggestions around these things. And the issues around choices is always subjective. Researcher bias, uncertainty. And the issues around making these choices. Okay, that's what I was saying. The issue around making these choices, like how big do you want the bandwidth to be? If you ask 100 people how big the bandwidth should be, you might get 100 different answers, which means you're going to get variation in the estimated treatment effect that is not being captured by the standard error. Okay, so to the degree that we can like find data-driven solutions to these things, then you take away some of the discretion, you take away the opportunity for p-hacking. Okay. So here it is. Choose the local polynomial p. That's really going to be the one choice you're going to make. Kernel function, we're going to say, we're going to give a recommendation. And, but for now, let's just say you chose the p. You say, I'm going to go to a quadratic. Now you're going to say, I'm going to go really high. And I'm going to choose the kernel, whatever it is. And I'm going to choose the bandwidth. All right. For observations above the cutoff, you're going to fit a weighted least squares model of y onto a constant and the recentered variable. You're going to get this predicted mu hat. You're going to have some polynomial that you chose. And here it's going to be like, the weight. And this is going to be the function that determines, this is the kernel function. Yeah, they're the same. They're exactly the same. And so here's that determines the weight on each of the observations. And so this right here, where what this is like using the data above the cutoff, this is your this is your predicted value of Y1. And when you do it below, it's the predicted value of Y0. And then you're just going to calculate the sharp RD at the cutoff. Okay. Meaning like you're going to use all these coefficients to predict Y hat at the cutoff. And you'll get a standard error on it, but you're going to be just focusing on that coefficient on the treatment variable. All right. So skip that. So here's like the boundary problems that I was talking about when you have trends. Here I have trends. So this right here is a, what this is right here. Okay. What this is I have a bandwidth of 0.5. Okay. I have a bandwidth of 0.5. And I basically dropped everybody else. Okay. Got a bandwidth of 0.5. I then just take the average under the rectangular kernel. No, it's not the intercept. It's the, you're going to be, well, in that example right then, it's just going to be here. It's going to be the difference in Y hat at the cutoff. So that it's going to be evaluated at the cutoff. And you're just going to set, you're just going to project, you're going to predict. Okay. So what you have now is, what? All right. So, okay. So you say, all right, I'm going to take my bandwidth to be 0.5. I'm going to choose a kernel where everything is being weighted the same. And I'm going to choose a polynomial of 1. Polynomial, no, of 0. Sorry. Polynomial of 0 means x to the 0 power means don't control for x. Right. So now are you going to, so what are you doing? You're taking the average of the outcomes within the bit, within the bin, within the bandwidth. Okay. And when you do that, even though the observations are following a trend, you took the mean, and at the boundary, okay, at the boundary, which this is kind of the way it's extrapolating. It's using all the observations, and it's like seeing where the mean hits at the boundary. Since they're all weighted the same, you know, the boundary is the same thing over here, but because there's trends, you know, like it's too high over here and it's too low over there. And so you found here that the Y0 was equal to A prime. You did it up here. You had Y1. And so you estimated the treatment effect to be A prime, B prime. But look, in reality, it was smaller. Okay. It's kind of the challenge here of like underfitting. Underfitting has this like, underfitting is going to lead to this boundary problem where you're going to end up with this bias estimate of the average treatment effect at the cutoff if there's trends. I see you typing, Jeff, so I'm going to. So the kernel function is one way in addition to the polynomials that you sort of deal that. I don't think so. I think that smoothness, I'm not positive about that, Jeff. I don't see why that would be true. Because I think that all of this holds under the smoothness assumption. But I have the book. I can look and just look at Cataneo and Titonic's book. But I don't remember. I don't think that matters. Would it be equivalent? Equivalent. Oh, that's interesting. Yes, that does seem right. Thank you. That does seem right. I didn't understand your question. Yeah. I think that's right. Unless there's some conditional randomization. But I haven't ever heard them talk that way. But you could imagine it. Yeah, but I bet you're right. It's just that it's only around the cutoff. So how far you make the bandwidth, there may not be randomization far away. I'm gonna have to think about that. You know, because the randomization is around the cutoff. I don't know how that interacts with the bandwidth. That's interesting. Yeah. Okay, cool. Well, thank you for saying that. So there's types of kernels. There's the rectangular, which we said is like a histogram, where everything, well, sorry. The rectangular gives the same weight to every observation. It holds even with polynomials. So it's just like the normal OLS models, specifications. Triangular and this one are different. Okay. So here it is, you choose a bandwidth, and when you choose the bandwidth, okay, you're limiting your data. For the uniform or the rectangular uniform, all of them are getting treated the exact same. So there's like observations in here, data. Every single one of them is being treated equally. It's very egalitarian, okay? But with these like kernel functions like the triangular, okay, what the triangular does is it draws a straight line from 0 to this point right here, such that they sum, I think, to 1. And so it's going to draw a straight line. And what it's doing is it's saying, well, if you're here, okay, if you're here, then you're going to get a larger weight, okay? But if you're far away, you're going to get a lower weight. And so in weighted least squares, this will just be handled, you know, mechanically with a weighted least squares approach. Epanikov, I have no idea. I've never heard anybody say it. So it forms more of a parabola, okay? So it forms more of a parabola. Ronald, you going to spell it out for me? So, so Cataneo, which one are you going to pick? And they show that if you use the triangular kernel, you can pick a bandwidth that is optimal. Meaning, if you use the triangular kernel, you can use a data-driven approach to choose what the optimal bandwidths are so that you're not choosing them. So there's this advantage to the triangular kernel in that it leads to this optimal bandwidth that will minimize mean squared error, okay, which is this bias variance trade-off, and you get a point estimate that's optimal. Triangular kernels assign 0 weights beyond the bandwidth, so like beyond the H interval, and so it gets positive weights within it. And so so that's what you're getting. I don't see people using it on this RD, and the reason why, I mean, it's offered as an option, but Cataneo kind of emphasizes the triangular kernel has like this, you know, unusual feature that Epi doesn't have, which is the triangular will minimize the sum of the bias and the variance, bias squared and variance. And so I think the uniform and the Epi do not do that. So if your goal is to use optimal bandwidth selection, then you want to pick the triangular kernel. And so this is what's interesting. If you decide to use the triangular kernel, if you decide to use the triangular kernel, then you can use a technique that will automatically identify how big the bandwidths need to be in order to minimize the sum of that bias and that variance term. And then the only choice you're making is the polynomial. And so it's a lot easier for people to kind of interpret and not think you're p-hacking. All right. So local linear polynomial, local linear RD, Taylor Swift has arrived at the Super Bowl. You saw that. Local linear regression discontinuity is the preferred method. This is where we end up in the world of choosing these bandwidths, H, and what that does is it controls the width of the neighborhood around it. All right. So I'm going to kind of skip here over to, well, let's take our 15-minute break because I really need to get into two things, the density test and the simulation. So let's take a break real quick, come back in 15 minutes. Okay. All right. 45 minutes. Let's go ahead and start. I'm going to skip over this optimal bandwidth and I want to get into the real core of things that I think are absolutely essential. And that is this one key test that I think you need to learn. And that is a density test that is used for evaluating whether or not the smoothness assumption is plausible. All right. So there's basically two challenges to smoothness. One is, this was brought up earlier. Yes, it's true. So this kind of idea, if you think back to what we've been saying, which is that the running variable in an RD selects the treatment for the person, right? Assume that's always true. But what if someone were to be able to choose their running variable value? Now, some stuff it's impossible. Some stuff that is impossible. If the running variable is age, you can't choose your age. Okay? If the running variable is income, to become eligible for a low income cash transfer, that's potentially something that's endogenous. That's endogenous because potentially, because you do have some ability, not perfect ability, otherwise we'd all be billionaires, but you do have some ability to manipulate your income. Okay, you could say to your boss, I only want to work 35 hours a week. You could say I only want to work 35 hours a week so that I have low enough money to qualify for a generous food stamp program in this state. Okay, you've chosen your running variable value, not by being dishonest. Okay, you're not lying on the form. You're not lying on the form about your income, right? That's not what it means to be manipulative of the running variable. You're not lying. You've chosen your running variable not by being dishonest, but by simply slightly reducing your labor supply. Okay, there's all kinds of stuff like that. Key was talking about using distance to the physical geographic distance from one part of a forest to a cutoff as a running variable. Depending on what's on there, depending on what's on that, what's being studied, you know, you might not be able to choose where you are on that line. But with human beings, you know, they try to choose stuff. So this kind of thing. So if the treatment is highly desirable and they know the cutoff ahead of time, and it's possible to move around on the running variable, you probably have manipulation or sorting on the running variable. And all this is really an extension of that selection bias that we discussed on the first day. It can, in principle, lead to a violation of smoothness, and it definitely, and using Jeff's point about local randomization, it's no longer the case that people just below the cutoff were randomly assigned there. Okay. Age falsification. Yeah. So like if you could have a fake ID, a fake driver's license, you could also manipulate it too. That's a good point. So there is ways to, yeah, good point. So there are ways. I mean, I had a fake ID. I haven't thought about that. Thanks a lot, Anthony. I hadn't thought of that in 40 years. I used to have a fake ID, and I was sorting on the running variable. You know, so like sorting on the running variable is basically the same thing as having a fake ID. Are you doing things that that allows you to choose your running variable value? And if so, then the running variable is endogenous. And if it's endogenous, you're not really solving the problem. You're not really solving the problem of the selection bias. Okay. So here we go. So manipulation of the running variable. I just said that. Here's the thing though, and I don't like this example, so I'm going to skip this, but here's the thing. If people are sorting on the running variable and they're choosing their income to be just low enough, okay, just low enough to qualify for that generous program, you, well, no, well, not to stay inside of the RD, because you've basically said that the cutoff, which is the instrument, you've said that the cutoff is no longer exogenous. So you could do instruments, you just couldn't do RD. You wouldn't be able to do RD because RD is saying that the running variable is assigning some units into the treatment. And that means you've got some people below the cutoff that are, you know, they are not being randomly assigned there, and they may have different potential outcomes than, you know, that is represented by that smoothness. Because in a world where they were not treated, they might not even be there. Okay, so that's the thing to think about. So if you see people though, imagine this. Imagine it's like you see people, all right, imagine like a bunch of ants, okay, in a straight line, okay? No single ant is like in one location, like no bunch of ants are in one location. They're not like a straight line versus like, say you put out like a candy bar and put it on the ground. What would happen? That straight line, you'd see all of a sudden a ton of ants right at the candy bar, okay? So this is a paper by Justin McCrary in a 2008 article that he wrote. And he suggested that, look, if people are choosing their running variable value, they know about the cutoff score, and they're choosing the running variable, and they want to qualify for the treatment, then probably what you're going to see is a bunch of people right there at the cutoff. So what he proposes is a density test, and now it's called the McCrary density test, although some people just call it the density test. I always like to give people credit, but some people will never give credit. So I like to say it. So assume a null where the density is continuous at the cutoff. That's what you're going to assume. You're going to assume this. You're going to say, assume a null where the density, which is the number of kind of a measuring sort of the number of observations. Here's a running variable. Here's like everybody over here qualifies for a generous cash transfer program. And over here, you don't. Under the null, this is like the counterfactual distribution. Under the null, if there was no program, you'd have some bell curve or not, distribution of income, okay? Some people who don't make as much money, there's like, you know, some mass in the whatever, okay? You can fit a line through it. And under the null, the line is like, you know, you can't reject the null. You can't reject that these lines are different from each other. This over here, let's say this is the real world, okay? This is the real world. This is what it looks like in the McCrary density. This is what it looks like if you have this problem. What it looks like is that these people that were right here, it's not that they're falsifying. They're basically, well, they might be falsifying. You don't even, here's the deal. They might be falsifying. They might be doing something legitimate. It does not matter for the design what their motives are or what they're, you know, or anything, or why they're doing it. It's just enough that they are doing it for some reason. Some could be falsifying. Some could be just reducing their labor supply. Okay. Some could be misreporting, whatever. So if that happens, these people, what they might do is they might just say, you know, I make $14,000 a year, where 14 is like just barely enough. Okay. So most people, when they like get a fake ID, they don't become like 30, you know, in the United States, they become just enough. And if you could get a distribution of like all ages of people at the gas station who have shown their card, if there was falsification, you might see well, you wouldn't see the problem is you couldn't do it because you couldn't see the 20-year-olds, couldn't see the 19-year-olds. So anyway, but these people are sorting. They're moving here. And when they sort under the null, that's the continuity of the density. And you're seeing if you can find evidence for that. Because if you can find evidence for that, then you may have found evidence to suggest that the smoothness doesn't hold. Okay. All right. I'm going to skip this. So here we go. Data visualization, and then we're going to do a replication together. So the first thing you want to do is you want to make pictures. All of your RD papers need to be very picture intensive. Okay. So you want to show your outcome by the running variable. It's always running variable and something. So if it's the outcome you want, you got to show the running variable and the outcome. All right. Now you don't have to show this line, but you're going to see people do it. So, you know, but be prepared. Some people might not like that you put the line there. There's all this like with RD, there is like all this like, there's a group of people with RD that always feel like when you put these lines there, they think you're like doing optical illusions. And you're like, well, if that line wasn't there, would I even see the cutoff? Would I even see the jump? You know, but the line helps identify the cutoff too. So some people, a lot of people will put the line. Okay. And fitting the data is not uncommon too, but, and I find it very helpful, but a lot of people won't put the line there either. They'll say, I'm not gonna put the line there because if you can't see the cutoff with your own naked eye, people will be skeptical. So just like with instrumental variables, people will tell all these narratives about exclusion. Well, it's not narratives here. It's more like if I can't see the cutoff with if I can't see the jump with my eyes on the outcome, I will not believe it. And that's very common. Okay, that's very common. Here's bin scatter. So with bin scatter, you're getting like a different binning based on the number of observations. There's commands for this, but I'm gonna skip over this. And here's RD plot, but I want to actually do RD plot. So secondly, but basically all this is me saying there's lots of ways to make this. You don't want to just do scatter. You want to do things that are creating means. Okay, so you want to there's a lot of data here, but so you got to create averages so that the reader can see what those means are. That's what this is. This is from Uber, and this is the surge generator. And when it goes above 1.25, they jack up the price. And so right here, the prices are higher than right there, and they used it to estimate consumer surplus and stuff. So you've got here this this fit, and it's not a polynomial, or it's just, you know, polynomial of 1. And so here you've got like, you know, not yet doing the interaction. Here's the interaction. Here is RD plot with a polynomial of 4. There's all these different ways you can do it. Second, you want to show if the treatment is not sharp. You want to show if the design is not a sharp design, meaning not everybody gets treated, okay, when it goes above the cutoff, then you want to show the first stage. All right, so this is like a study done of people that enrolled at the state flagship school at a university when their test scores shot above the minimum number. Okay, they shot above the minimum number, and you saw here that it went from about 10% to 50%. Some people still got in; they were probably like athletes or something, or it may have been, you know, something that was like needs based. But anyway, shot up about 40 percentage points when they had the minimum SAT score. You want to show it. You want to show people that there's a first stage, basically. Density of the running variable, you got to show that. Every one of your RD papers has got to have this. Everything I've discussed so far is mandatory. You got to show that. Covariates, very common. People will also evaluate smoothness by looking at covariates that are highly correlated with potential outcomes. Because if potential outcomes jumped, smoothness didn't hold, people think the covariates would have jumped. So even though you can't observe the potential outcomes, you can observe the covariates. So people will do that too. And you want to see smoothness in the covariates. All right. So here we go. Let's look at, well, no, they're not. You do, I kind of skipped it, Eduardo, a little bit, but when I was going over, when I was sort of went a little fast, but I was worried I didn't have time. So yeah, with these non-parametric methods, okay, you can get these asymptotic 95% confidence interval for an RD. It's going to be too small if you ignore the bias and variance terms when you're doing these like kernel-based approaches, these non-parametric kernel-based approaches, if you ignore it. So there is like a valid, robust, a robust method that will be efficient, that will be correct coverage. So the bias term, it's gonna, you have to kind of, there's a lot of different strategies that's done. This one, the conventional confidence intervals, is not usually considered to be credible. That's the one that's kind of standardly reported. There's a bias correction term, which will like correct for the bias in the approximation of those potential outcome functions that you'll want to kind of estimate, and then you don't have to do it, but it's standard package. And then there's one that also addresses the variance term. Okay, so there is things like that, and then there's also things where people have clustered historically on the running variable when it's got this multi-valued running variable, and that turns out to be a little complicated too. So there is a little bit of work out there on inference. There is a little bit of work out there for inference, and so Causal and Roth, they have their own sort of criticism of using clustering, where you cluster on the running variable. And problem is it will have over rejection problems. Standard errors will be too small if it's a multi-valued running variable. And they propose these two alternative confidence intervals called honest. There's a package for it. Okay. So, you know, I think RD robust is probably another reason to use RD robust, is that you can get these correct, you can get correct inference with these non-parametric methods. But I want to show you, this paper that we're going to do together. Okay. So this is a paper by Benjamin Hansen. He's at the University of Oregon, and it's called Punishment and Deterrence: Evidence from Drunk Driving. All right. So Gary Becker, who I mentioned on day one, he says, you know, crime, you make crime more expensive for a criminal and he'll do less of it. The size of it, who knows? They could be completely inelastic, though. It could be like, you know, if you make punishment more severe, could be possible that people will not reduce their crime. That would mean they have an elasticity of 0. That's not crazy. People with diabetes have an elasticity of 0 for insulin, you know, up to a point. There's a point where they have to, but then they're not going to be healthy. They may not survive. But there are people like that. But Becker said, well, it's downward sloping. And, you know, that's like a whole body of work for like 50 years. 60 years, 55 years, has been about, you know, is there evidence that if you make crime more expensive, you'll get reductions in crime? And the problem is, like in the real world, when you make punishment more severe, typically what happens is two things will happen at the exact same time if you make punishment more severe. One is, Becker says, you're going to reduce crime simply by making it more expensive. But if you punish people more, you could reduce crime simply by removing them from society. Okay? And it's technically not the same thing. Because if there is evidence for deterrence, it kind of has like implications for designing deterrence-based policies. But if there's literally no evidence for deterrence, you know, it won't work. And so then the only thing you can ever do is this, and people have opinions about that. Okay. It's expensive, things like that. So let's look at what Ben does. Ben is going to find evidence for deterrence. I'm not positive he is finding evidence for deterrence, but he is definitely finding, I think, causal effects. There's a lot of stuff that ends up happening. I'm not positive that this is deterrence. But anyway, let's see what he does. The United States has a minimum age of drinking at age 21, like we said. I'll show you just a second, Eduardo. We're going to have it in the data. We're going to have it in my package. So early studies show that minimum age of drinking was associated with higher mortality, like we showed, due to drunk driving. Okay. Washington State, which is a state, for those that aren't in America, there's a state in the United States at the top left part of the country. It's called Washington. It's where the mountains are. It's near Canada. And they passed a law. Well, no, sorry. They didn't pass. Everybody has this law, which is that if you're, when you get pulled over by a police officer and he suspects that you're drunk, if he suspects that you're intoxicated, he has a machine. You blow into the machine. In your breath, it analyzes the blood alcohol content in your breath. I don't know how it works, okay? But the measurement is called blood alcohol content. There's a number, and the unit of the number is like a percent of blood alcohol content. I think it's a percent. It's a unit. You know, it's a unit that's measured in terms of blood alcohol content. And America has a law pretty much across every state, I think. There might be more extreme versions of this too, but if your blood alcohol content is above a 0.08, you will be legally treated as intoxicated and you will get an arrest pretty much. I think it's sharp because they do not have discretion in the United States to not make that arrest. They pull the breathalyzer out, whatever happens is going to trigger the arrest or not. So if you have a 0.07, you don't get, I don't know if they can arrest you. If you have a 0.08, they have to arrest you. Okay. So he got data from Washington State, 512,000 observations. That's what we're going to look at. So here's the policy. And I'm going to not look at that one. All right, here's the policy. If you get arrested with a DUI, okay, we're gonna only look at this one. Okay, so we're only gonna look at the regular DUI. You can do all of it yourself, but we're not gonna do it. So if you are arrested with a DUI, okay, meaning your blood alcohol content is between a 0.08 and a 0.15. Anything over 0.15 gets an additional one. Here it gets an aggravated DUI, but we're not going to analyze that. He finds it for both. You're going to get a DUI. Your minimum penalty is you have to pay $865, and the maximum penalty you have to pay $5,000. The minimum jail time that you can do is 24 hours in jail. The minimum home release, 14 days. You can do that instead of jail time. You have to have your license revoked or suspended, okay, for 90 days. And you have to get this insurance. Now, if you get a 0.08, you're going to go over here. If you get arrested again, you're going to get a second offense. But if you get a 0.07, you never got arrested. So a lot of this analysis, when you think about it, is that two people get drunk, okay? Person one blows 0.07, no arrest. Okay. Person two blows 0.08, arrest. All right. No arrest. If they get pulled over a second time and they are found guilty, then then it'll be their first offense. Okay, first offense. If this person gets pulled over a second time and are found guilty, it'll be their second offense, even though they're basically identical. On average, the people that got a 0.07 and the people that got a 0.08, it's so small that it seems like it would be almost impossible to manipulate the running variable. Okay, not like, because like people that are drinking and driving, it's not that easy to get that close. If you want to manipulate the running variable, you just don't drink and drive. So if you are this person, if you're person 1, you never got the first offense, so you're just going to do it again. If you're person 2, you got the first offense and you're down over here if you get arrested again. If you blew a 0.079 and it showed up as a 0.079 on both of the machines, they'll do it twice. If it shows up both times as a 0.079, I don't think they can get arrested. Because it's going to go before court. Technically, 0.079 is not illegal. So, so here you got, this person blew a 0.08. Let's say this person blew a 0.079, like Shreyoshi said. So second offense, they blew a 0.08. They're now eligible for a second offense if they do it. And if you go for a second offense, look what happens. Your minimum penalty has gone up by about $300. Maximum is the same. Your minimum jail time, though, is now a full month in jail. Minimum home release, 60 days. 2 years of your license revoked. Okay? So that means this. Of the 2 people committing the DUI, a second time will result in a larger punishment for person 2 because their drinking was illegal, so they got arrested. Or was it a larger punishment than person 1 who their drinking did not result in an arrest, so they're still on their first offense. So Ben kind of found a pretty clever situation where he could look at 2 groups of people that are basically, they appear to, he's got to check to see if they're like equivalent groups of people, but it appears like they're going to be equivalent groups of people, one of whom is going to face for drinking a punishment here, and the other is going to face a punishment here. Okay? He's just got to figure out how he's going to work with it. So here's what he's going to do. He's going to create a histogram, right? He does not do the density test. He does a flat out histogram. This is what we want to look at. There is growing numbers of people that have very large, high blood alcohol content when they were pulled over. These people were not arrested. And so these people right here are arrested, but there does not appear to be a spike in the number of people like on either side. All right. So here's what we're going to do. We're going to go over here into Causal 1, lab, DUI recidivism, Hansen.do. All right, Hansen.do. So I'm going to use Hansen long, but if you look, actually, if you look, the R package is here too, Hansen.r. And then there's the solutions over here. You got a markdown for all of them. Okay. So let's look at what we're going to do. So I'm going to do all this so that you can see it. So you got to delete all this and you got to install like 6 different packages. I've already installed them. So here's the data. Okay. So I got it. See what we have. All right. I got a date. I got this alcohol 1, alcohol 2. I don't remember what that is. I don't remember what that is. But I've got here, I'm not going to use low score. I'm going to use male, white, recidivism, accident, their age, year, and then we're going to use back 1. Can nobody run this? When you run this, it doesn't work? Is anybody able to download this? Did you run it? Shrey O'Shea, did you run it manually? Like with the do like that? Jeff, are you able to do it? Yeah, I think Shrey, you might be typing it into the command line. You've got to make sure you're doing the whole thing. Ah, there you go. Okay, so here's what we're going to do. We're going to make this picture. Okay, we're going to make that picture. Histogram back 1, discrete width 0.001. The reason we're doing 0.001, why are we doing 0.001? Because the bend width is 0.001. All right. Original precision used on the breathalyzers is 0.001. So that's what we're going to do. We're going to put the X line at 0.08. Let's see what we have here. All right. So what Ben wanted to do, I saw Ben present this one time, and there's just like, again, there's just a group of these applied people that really prefer to do stuff like non-parametrically. And so he's just like, look, I'm not going to do a test. I'm not going to do the density test. I'm just going to show you the raw data. There's no jump. Okay. Now, what I'm going to do now is I'm going to create a dummy variable if your blood alcohol content is less than 0.08, and it's going to be equal to 1. If it's 0.08 or larger, then I'm going to recenter it. And do it again. Now it's recentered at 0. Okay, it's recentered at 0. We're going to use that later when we run our regressions. Now I'm going to do RD density, a density plot. We're going to see if we can reject the null. Okay, and we get this plot here. And now there is these weird patterns. And to this day, I really do not understand what is going on here. There is some kind of weird, heaping thing that's going on. And it's like non-random. I don't understand why it happens like this. So I don't really know what to say there. Okay. But I'm going to move on. Second thing that Ben does, okay, second thing Ben does is he runs local linear regressions on a chosen bandwidth. He just picks a bandwidth, okay? What is his bandwidth? His bandwidth is 0.05, 0.05 from the cutoff. So the cutoff was blood alcohol content 0.08, and he says, I'm going to go left of that to 0.03, right of that to 0.13. That's what I'm going to run, and I'm going to run a regression on covariates. Now he gave me this data, and I only have it for those 4 things. Okay, couldn't give me this. My data is, there's less of it. So I got male, white, age, accident. Okay, I'm going to run that, and I'm going to run it from right there. Now it's going to be different than he found because the data he gave me is a little bit smaller. I have 6,000 fewer observations right there. In fact, he had 512. I have half of it. He wasn't able to share all of it. So look, what is your interpretation? I interacted the dummy variable with the treatment. Sorry, I interacted the running variable with the treatment. All right. And I limited the bandwidth to 0.05. 0.05 before, 0.05 after. All right. I did it with this recentered variable. It's a recentered running variable, which is going to allow this interaction. The recentering is going to allow the interaction to only identify the parameters above. Okay. So here's what you find. 0.006 with a standard error 0.006. He found 0.007 with a standard error 0.005. You've got, you know, a precisely estimated null effect. There is no difference between in the average number of men above and below the cutoff in that, you know, that bandwidth. Okay. So now we're going to do white. 0.0057, 0.005, 0.002, 0.005. And you can see here he's reporting the mean. So on average, 79% of the people with a blood alcohol content of 0.079, 79% of them are men, and just above it goes from 79.2 to 79.9. So it doesn't really do anything. Here it goes from 0.852 to 0.854. That's not doing anything. And the average age at 0.079 is a 34.9-year-old, and at, you know, above the cutoff, it's a 34.75-year-old. So I do all of them. I do accident too. You can use the constant right there to get the mean. It's not really changing. So the magnitudes are not very big, okay? But now I'm going to make some non-parametric pictures, because he's going to make non-parametric pictures too. He's going to make a male, an age, white, and accident. So let's see if we can make it. So I'm going to make it using a command called CMOgram. You can look in R and see how it's done there. I'm just going to make it here. Now, CMOgram, I think it was made for RD, but it uses an automatic binning. Chooses the bins. So here, here you see here for male, 79. So there it is with using that linear fit. Okay. I'm going to do it again. No, that's, oh yeah, that was male. And if I want to do a quadratic fit, I can do that too. It's weird. I don't even remember doing this weird color. I guess I did it somewhere earlier. So here we go. And so you can make it for all of them. You can make, so that was male. And it was like, looks a little different. Why was it so different? I don't really know why that's different. Let's see what this one does. White. Choosing a ton of, I'm choosing a ton of bandwidths or bins. Something seems different than normal. I'll have to dig into that. But anyway, I think you can look at it, CMOgram. I think you might be able to pick your own bins. Control the bin definition. Oh, I bet that's it. Bins. Did I do it somewhere? I'll have to play around with it. Anyway, you can go through and do all of them, okay? All right, so let's look at like what he does next. So what he does next is he now is looking at the effect of getting a larger, getting the blood alcohol content of 0.08 versus 0.079. What's the what percent of those people who get the 0.08 commit a second offense? He's got a recidivism dummy variable. I have it right here. Recidivism. Tab. Recidivism. Recidivism means committing a second offense, getting another DUI. Okay. Showing up in the data a second time. Now he does this right here. Okay. And he says he's finding that when he does it, there is a 2 percentage point reduction in DUIs for somebody that just barely got a DUI. off of a mean of 10. So it's pretty big. So let's look. I'll do it right here. Main results. Let's do it right here. Okay, so I'm gonna go recidivism. All right, run that regression. Mean of 0.11, mean of 0.10. Treatment effect, 0.02 off of 0.11, 11.117, 0.0236. He finds 0.021, highly significant. Okay, but maybe there's linearities. All right, maybe there's linearities. So what I'm going to do is, I'm going to, do I have a blood alcohol content one? So I'm going to go here, and I'm going to say Gen BSQ, back one, SQ equal back one squared. Okay. Put a quadratic in there. It drove it down, but it's still highly significant. He doesn't do that. He doesn't do that. Okay. But I did it. He then makes these pictures. So I'm gonna make some pictures too. Bin of 30. Maybe that'll look better. So this is what his looks like. Okay. But I just put in the linear fit. So now I'm going to put in the quadratic fit. I'm only allowing 30. See that right there? I'm only allowing 30 bends. So it's doing this like automatic bending. So you can kind of see here that there appears to be something there. The boundary minus the boundary. What is that? The boundary minus the boundary is that. Okay. So what I'm going to do now is, oh yeah, I did it down here. So that was it. What I'm going to do now is, I'm going to use the RD plot. RD plot lets you use these triangular kernels. So I'm going to put one polynomial in, which means it'll be a straight line as a function of the running variable. RD plot, recid, back one original for this. And we got the cutoff at 0.08. And we're going to allow one polynomial. We're going to allow the triangular kernel, and we're going to be minimizing the mean squared error on both sides. Straight line. Okay. Let's do it again. RD plot with a quadratic. P order 2. With the triangular kernel, which is weighting the observations higher at the cutoff. Quadratic. You can go to 3. You go to 10. But you're now getting into that world of overfitting. But let me show you what overfitting looks like. I wouldn't even do it. So it disobeyed it. So, okay. So now let's, do the, RD robust. All right. So look, here it is, RD robust. all right, RD robust using the kernel, minimizing mean squared error. And I said, report all of the standard errors that we had talked about. This one's not correct. Standard errors are too small. Confidence intervals are too narrow. Bias corrected only addresses the bias, gets a little bit of a smaller, once it starts doing this, it's adjusting for that. And then we're getting slightly more precise. That's surprising. I don't remember why it does that. And then the robust adjusts for the bias and the variance. And we get even bigger confidence intervals, but that's to be expected. Oh yeah, because the bias is adjusting the coefficient, and the estimated variance is addressing the coverage. So here, 0.018. 1.8 percentage point reduction in recidivism, okay? And to figure out what the normal is, you would just say something like summarize recidivism if back one a ridge is greater than or equal to 0.07 and back one a ridge less than or equal to, less than 0.079. You'd say, all right, it's on average right there, it's 11.5 and it fell 1.8 percentage points. So it goes from 11 to 9 something. Okay. So I can go, all right, do a higher order polynomial, report all of them. As you put in higher order polynomials, it's going to always increase the coefficients. And it's going to change the bandwidth. So where's H? Here. Okay. So I'm allowing for the bandwidths to be different on either side. I'm going 0.03. The bandwidth is 0.033 from 0.08. But on the right, it's going further, 0.054. When I used a polynomial order of 2. But when I did 1, it used less. So the more polynomials that you put in, the optimal bandwidth ends up growing. It ends up getting bigger. So if I want to do it even bigger, go to a quadratic. Okay, it was 0.033, 0.054. .038, 0.094. Still though, getting pretty much, it's not really changing. Okay, it's not really changing. So let me tell you the concluding remarks. RD is a surprising method for being so popular and so powerful. Oh, it's surprising because it's really not, it's pretty straightforward. All it really is like, look at the averages to the right, look at the averages to the left. It's really, that is basically it. But it's trying to figure out how you're going to handle the boundary problems. So there's all these like little fixes that are done, quadratics, kernels, bandwidths, whether you're not going to use global or local regressions, and how you're going to do inference. All right. You need to have strong visuals, particularly on the outcome. People have to look at your data. And when they look at your data on the outcome, organized by the running variable, left and right, the cutoff, they have got to see it with their own eyes. When they really don't see it, by and large, informed people become, pretty skeptical. I feel like I'm not the best judge because I'm a fairly generous person, but that's kind of the where we are. So in conclusion, I guess I don't have a really great concluding slide, but in conclusion, the RD method, very, very powerful. IV method, Yes, I wrote it down, Eduardo. I got to check with Keith Finley about what I can share, but it should be fine. I think I can even share the original data. I just got to ask. But so the thing to be thinking about from all this is being able to interpret as you're doing these studies, making sure that on the front end you define exactly what your parameter is. Define what those assumptions have to be, build the estimator around those things, and constantly be thinking about, the big picture, which is what is the mechanism that is assigning these units to treatment. And really, for what we covered, there was just 5 things. Rationality, which is the bad news, creates all this selection bias. Randomization, great if you're an experimentalist. If you're not, then you've got covariates, instruments, running variables. Okay. And those are the things. And all of these kind of have useful uses of randomization to a little bit of a degree. The smoothness part is a bit of a modeling assumption, but there are people that will talk about regression discontinuity design as randomization around the cutoff. But you can see here in all of this, what you're doing is you're not really modeling as much as you are taking advantage of a known treatment assignment mechanism, which is a little bit different. This part of causal inference is a little bit different than how I think we're taught it usually in our stats and econometrics classes. Okay. All right. I've kept you over 6 minutes. Thanks so much for the workshop, for being on it. And it's going to take about 3 hours, but I'll get this posted as soon as possible. And I'll start asking Keith if I can share the IV paper. All right. Bye, guys.